Now we're going to get into a little more complex. We've talked about resistance, inductance, amperes, current, voltage, and all those kind of things. We're getting into there are types of resistance. You shouldn't say that, but they kind of form similarly to resistance, but they have other characteristics. And one of those is called reactance. Reactance also impedes the flow of AC current, not necessarily DC current, but AC current. It results from energy storage in a field. It uses the electric field for capacitors and the magnetic field for inductors. And the amount of reactance depends on the frequency. So you can have, as you see from the bottom, you can have inductive reactance, that is reactance caused by an inductor, or you can have capacitive reactance, that is reactance caused by a capacitor. And the unit is the same as for resistance, because in some ways it behaves as resistance. In fact, you can see it it uses X as a symbol, but it replaces R in the Ohm's law circle. Okay, reactance and impedance. So a resistor current is in phase with voltage, and a capacitor, the current leads the voltage, and an inductor current lags voltage. So resistance combined with reactance forms impedance, which is Z. Remember, we got X is equivalent, X is reactance, and impedance is Z. Z is in opposition to AC current flow, and again, the unit is ohm. So both reactance and impedance are similar to resistance. They're in opposition to AC current flow, because see, we're talking about phases here, plus leading current or lagging voltage. You can't have that in DC. You only have that in AC. So both reactance and impedance, you know you're dealing with AC power if you have either of those parameters that are part of the question. Resonance is like the tone of a guitar string, or if you watch a clock pendulum go back and forth, you're seeing things that are resonant. A sustained oscillation at a particular frequency is resonance, and the amplitude, though, generally decreases as the energy dissipates. For instance, getting back, many people see these and they think that the thing is perpetual, but it's not perpetual. People actually have to wind these things up and actually give the pendulum a swing to keep them going. They're very low friction, which friction being the mechanical form of resistance, but they're not perpetual. So they do, as this says, the amplitude of them gradually decreases as their energy dissipates. And here shows the potential energy of a vibrating string versus the kinetic energy. So you've got, when it's at the resting point, it's all potential energy, and when it's at the either side point, then it's kinetic energy. Okay, a resonant circuit. Now we get into the whole reason we have to worry about resonance and all of this, which is because we need our circuit to be resonant at a certain frequency. So we need the ability to have to be able to select a frequency that we want the circuit to operate on. So a capacitor and an inductor can be connected in series or in parallel to form a tuned or resonant circuit. So you set the operating frequency of the filter, and the oscillator circuit is why you do that. So if you want to make a filter that will block certain frequencies of voice, for instance, in many cases, speakers that work out well for stereo, for music, have a lot of high frequency capabilities. That's not good for communications, because about what you're going to hear in the high frequencies in the communication is noise. So one of the ways to stop that is to build a resonant circuit in the case of a filter, and you can build those in series or parallel. In this case, parallel, and you select an inductor, you select a capacitor, and you tune that to essentially attenuate. There's what's called high-pass filters, low-pass filters, etc. In this particular case, you want to build a low-pass filter. We'll talk about that more later. That will allow all the lower frequencies to pass, while the higher frequencies would be attenuated. So it would make the communications clearer because you clear out all the things that don't really contribute to the communications. Capacitor and inductor uses, power supplies. When we talk about a power supply, one of the things that you do, the two things you have to do is create, let's say, the 120 to 12 volts, or 120 to 12 volts, or 13.8 volts, or whatever you want, is you've got to get the transformer we just talked about will get the voltage down, but you've still got a sine wave AC current that you want to make into DC current. So this is AC current, not terribly well, and then this is 0. And then what you really want, though, is just a solid current. Well, there's something you can build, and we'll get into that just a little bit, is a rectifier that will take this part. First of all, the first thing it does, you can get a rectifier that's what's called a half-wave rectifier that essentially will just eliminate the bottom part. Well, then you've got essentially a pulse, almost like DC, but it's like a pulse. Well, that's some circumstances can stand that, but then some take the bottom half of the cycle and flip it. That's a full wave rectifier. But even here, you don't have DC. You've got these little valleys. Well, that's again, you build in a power supply. You put a filter in that will essentially filter this out, and essentially levels this out to where it's not nearly as bad. It's not perfect, but it's essentially very good. The filter can make it look like what was an AC current has turned into a DC current. So that's the reason you put capacitors and tune circuits in power supplies. You're trying to use them as filters to filter the current to get it to where it gives you what you need, or close to what you need, at least what you can use. Another point for them, antenna tuners. Generally speaking, we talk about how the wavelength is one particular frequency. Typically, your antenna is a perfect match at one specific frequency. And as you move away from that frequency, it gets to be a worse match. Well, you can tolerate a certain amount of mismatch, but then once it gets too far, your transmitter won't be able to handle it. And we'll get into that later as well. Well, what the tuner will do is essentially tunes the antenna to where it provides a match that the transmitter or transceiver will tolerate. And so in that particular case, an antenna that wouldn't work suddenly will work, or at the frequency that you need it to work. So antenna tuners, again, tremendously important area for tune circuits. And RF power amplifiers, we've mentioned those previously. You got to have those tune circuits in for that. Oscillators, which are kind of the basic building block of all transmitters, or really transmitters and receivers both. So they will do that. So really the whole concept of inductor and capacitors and tune circuits are kind of the basics of radio. But a diode is essentially a silicon junction that lets current only flow in one direction. So in one direction you get a large flow, and in the other direction you get essentially no flow. This is one with forward bias. So that can be useful. Actually, in the mechanical world, it's what we call a check valve. It's like what we call a check valve, which allows fluid to flow in one direction, but then when it tries to flow back, it gets stopped. So again, the fluid to electrical analogy can still hold. A reverse bias allows almost no current flow in the reverse angle, but current flow in the in the forward angle. So these are used in power supplies. Actually, as a rectifier, I mentioned rectifiers. The diodes are used in rectifiers to help. There's, like I say, a half-wave rectifier, which only gives you what's the black portion you see here. And then the full-wave rectifier gives you the full output that we see there, which is, again, much easier to try to use as DC voltage than just a half-wave rectifier. And of course, the thing we all deal with now is LEDs, light-emitting diodes. They've largely replaced incandescent indicators on radio gear, and they're rapidly replacing fluorescent tubes and incandescent lamps in your home and office. That's one of the things we're doing a lot of at Fort Bragg now, is replacing fluorescents with LEDs, because the price point has dropped down below where the cost to replace can be justified by the cost of the energy that's saved. And so we're installing a bunch of those. So I remember the early LEDs were only available in red now, but turns out getting an LED to white has been one of the more difficult obstacles they've had to kind of try to overcome. But they've managed to overcome that now, and like I say, even do it in a pretty cheap fashion. So now you get LEDs with just about any color you want. So they're taking over everywhere. The next step beyond the LED is a transistor. A transistor is essentially a diode with one more lead to it, and it can do something even smaller, even greater than the diode can do, and that is it can amplify a signal, or it can use a small current to control a larger current. Well, between the two of those particular things, you can accomplish most of what you need to accomplish in the electronics world, is the ability to use a small current, control a larger current, and then to amplify and switch. So in this particular case, you've got a PNP transistor, and you have a large current goes in this way that the small current is controlling. Or in this particular case, you've got a small current in the NBN that's going through this way, and it's being amplified by a large current. So they're again, two of the basic building blocks of what we're trying to achieve with in electronics in general. Then there's something called field effect transistors, FET. And in that particular, we show them here in the gain of small voltage controls a large current, as we talked about, and also in amplifiers and switching. The open end in this particular one is called the source, and the closed end is called the drain. By the way, I didn't go through that. Let me get back to that here. You've got the base. In this particular one, you have the base, the emitter, and this is what's called a bipolar junction transistor, BJT. You've got the base, the emitter, and the collector. That's the three parts of a BJT transistor. So that's something that you will need to know ultimately. So we want to make sure I covered that. Then with transistors, you've got the source, the ground, and what's the D stand for? Drain. Source, ground, and drain. So that's what this particular units are. And again, it works in a similar fashion. Off the top of my head, I can't remember. There's certain situations under which the FETs work better. FET is more of a kind of a newer type transistor than the BJTs or BJTs, and but they are much more efficient in some ways. So that's why they're used in situations where the other ones wouldn't be used. Now, when we're talking about components, the terminology of the components is that the electrodes are the terminals or connections to the various parts of the components. We speak about electrodes connected to the cathode or the anode of a diode or to the emitter, collector, or base of the BJT. So electrodes, we call, the more common people call electrodes, the leads or terminals of the component. So that's particularly, that's the component terminology. If you want to see what some transistors can look like, small specks on the surface, they're actually surface mount transistors. These are like power transistors. This one in the upper right can dissipate 100 watts. This is a little bit smaller, but you'll see the hole here. What you generally will have bolted on there is a metal frame, a little metal frame that is essentially a heat sink. It allows the heat to dissipate from the transistor and get rid of the heat, because heat is the enemy. In general, heat's the enemy of electronics. So whatever you can do to get the heat away is worth doing. To show you just how small some of these surface-mounted transistors can be, there's a penny. And this little one over here, that's a transistor. So that gives you just some hint of how small they can be. This also tells you why a lot of people, they're not dealt with. A lot of these type of transistors are actually installed by machines. They're not even installed by humans. So integrated circuits combine many circuit functions in a single package. Generally, they have many transistors on them, can have up to millions of transistors on them, as well as resistors, capacitors, all at microscopic size. Fuses, speaking of not having your radio failing, fuses do lots of good things. First of all, the most basic level, they prevent fire hazards. They prevent equipment damage due to high amperage. But when you replace them, you should never replace them with a higher current rating. So this is what the schematic symbol for a fuse typically is. This is some other alternatives, but this is what you'll mainly see. These are fuses like you see in your car. This is a big fuse, big bus fuse. These blade fuses are typically used in automobiles. Sometimes you still see the little fuses like this that are put in there. This is actually an old style fuse that you used to see in homes. In fact, the house I grew up in, we had a fuse box of these in them. And the bad and good thing about them is they screw out kind of like the top of a Coke bottle. And what people could do if you didn't have a fuse is you could put a penny in there and just screw it back in, and it would keep working.
Forever.
For a while. Yeah, for a while.
Until the house burned down. Until the house burned down.
Yeah. That's right, until a house burned down. Well, there's also other alternatives you can have for fuses. This gives approximate amperage ratings. I think that's like a pin, that's about 100 amp. If you crumple up foil, we've got 250. If you use like a 308 rifle cartridge, that'll give you about 350 amp and an audio visual alert, whatever it's and they hold about 600 amp and a bigger bolt, and then this, and a 16 amp and 130 amp. So that gives you approximate ampere ratings of various replacements. And believe it or not, having worked in industry and now government and whatnot, but I've done a lot of energy audits on industries and whatnot, you see stuff like this. Actually, you don't ever see, I've never seen a rifle cartridge used, but you see lots of stuff like that haywired in together. And it's always, where I do it or anybody do, it's always, I'm going to come back and fix it in just a little bit, but I got to get it running right now. The problem is come back and fix it later never happens until it fails catastrophically, and then you lose whatever it is. So anyway, that's just some fuse alternatives you want to be sure you don't use, and you hopefully if you see somebody else that's used them, you point it out and get it fixed quickly. Circuit breakers, that's what you generally use at home now rather than fuses, as we were talking about. It can be reset, so you don't have to have a new fuse to replace it. Ground fault interrupters are also something that you have in most bathrooms now, kitchens, and places like that. That takes a very small ground fault, will trip it and protect you from getting shocked. One of the reasons why you see them in bathrooms and that kind of place. So they're both, again, fuses and circuit breakers are there to protect you and your equipment. you abuse them at your peril, at your risk. Switches. Well, a fuse is a switch. So it switches everything off. It's essentially a single pole, single throw switch. But of course we don't want to always have to use a fuse. So essentially if you want to turn something on and off, a lamp is a resistor in and of itself. That's not too schematic for a lamp. So you've got a battery, you've got a drop-in resistor, you've got a lamp, and you've got a switch. So you want the switch off, you pull the switch open, and that's how it looks like. That shows it in an open position. Typically on schematics, they are shown in an open position. The idea being you can pretty much figure out when it's in a closed position. Well, this is a simple single pole, single throw, turn something on, that either makes the circuit or breaks the circuit, as in this little circuit here. Single pole double throw can make one circuit, or it can flip down and make another circuit. Maybe you've got two different lamps. You want to switch from the green lamp to the red lamp, or whatever. That's what single pole double throws can do. Then you can get really more and more complicated. Double pole single throw, that can turn on and off two circuits at the same time, rather than just this one circuit. It would, if you got them ganged together, as you see the dotted line there. So when you flip the lever, you're actually flipping two switches. You're making or breaking two contacts on two circuits. Then there's double pole double throws, which can be used, as in this case, to choose between two different circuits. It also can be used to choose between four different circuits. You can get really complicated once you start getting into the multiple throw switches. But what the test wants you to know is just have a general knowledge of how switches work and what they're used for. Then you get into really complicated switches. This is where you have rotary switches that can switch from one to several circuits, and then you have them ganged together. So as you turn this, it makes one switch here, one there. It's generally like they were saying, fan switches on a radio or something where you want one turn of the switch to change several circuits simultaneously. So this is just some pictures of some switches. This is just what toggle switches, push button switches. In push button switches, you might be aware that there's momentary on, which is to say, as long as you have the switch depressed, the circuit will be on. Then there's also on off. There's essentially where it toggles on. One press turns it on, the second press turns it off. So there's a number of ways they can be wired and put into the system. But that's just some general switches. Most of you have seen those. You've seen the outside of them. You've seen the switch part. You may not have seen the part behind it that actually gets the job done. Relays are a switch controlled by electromagnet. We talked about them briefly a minute or two ago. Essentially, you have a coil that, when it is energized, it magnetizes, that pulls this metal switch and makes contact. And so what it means, actually, one place that you use electromagnetic switches or relays is to have a small current turn on a big current. And that's, so essentially, just like we were talking about with transistors, something they can do is you can have a 12-volt line here that energizes and causes this to switch, and this may switch a 220-volt power in a welder or something like that. So it allows you to have the button you're touching only has 12 volts on it, but it may be controlling a circuit that has is much more powerful, much more a higher voltage. So that's what some of the relays look like. This is little cube relays. You see those in a lot of different places. And some of them, this particular one is soldered at the bottom, but you even have some, I don't have a picture of them here, that are actually put in sockets, that you actually just put the relay in a socket, and if you need to change it, you just pull it out. You don't even have to do any soldering or anything like that. Okay, ground. There are two types of grounds you may encounter in radio and electronics. One is the earth ground. That's what we might call the real ground. That's connected to the dirt. That provides you with electrical safety primarily, because essentially it can reduce shock hazard by providing a path for the electricity to go to ground and dissipate rather than going through you. And it also can help minimize voltage differences between various pieces of equipment and you. It can help reduce lightning damage because essentially, again, it reroutes that heavy current from a lightning strike in a way that is less harmful. I won't say 100% harmless, but less harmful than otherwise. Yeah. But anyway, this shows ground and ground cable. This is the schematic symbol for ground, or earth ground. Now, chassis ground. This used to be more of a point of contention than it is today, but it's a common point in the circuit. Now, this is an older radio that has a metal chassis. And so in many cases, they would use the metal chassis as the current return to the power supply. And the problem is, if you're dealing with an older radio, sometimes that's used as the return for 120 volts. So if everything's working perfectly, you're okay. But if anything fails, one of the capacitors fails or whatever, you can get shocked pretty heavily. I guess you have some gear like that. Some of the older gear. Now actually they use what's called isolation transformers as one way to try to make them a little safer. But that's where a lot of this started. It's a way to save money because you essentially, rather than having to run a second wire and everything, it's like on your car. Some people use that on their car. Cars are harder to do that way now. But you get the positive from the battery and you just ground it to the car ground. Well, now there's so many non-metallic pieces in a car that what you have may not be grounded back to the battery, the piece of metal you're dealing with. But that's one thing that people do. Now on circuit boards, it's usually a common track or a trace on the circuit board. So they still have a chassis ground. You can still have a chassis ground, and that ground may or may not be connected to the earth ground. It is safer if it's connected to the earth ground because, again, you don't have to dissipate the electricity under emergency conditions, but it may or may not be. And this is the symbol for a chassis ground as opposed to the other one that you saw for earth ground. Okay, so miscellaneous symbols. Actually, that shows that as an incandescent light. I've always seen the incandescent lights used as a curl, like I use there, but that's another possibility for incandescent lamp that might be behind your multimeter on a rig. This is like the multimeter on the front of a radio that can actually tell you several things. And like this 0 to 250 watts, 0 to about 30 dB, SWR here, etc. These are like what you see on the front of a typical radio nowadays. Except now, actually the newest radios, you don't have those meters anymore. Nowadays, on the fronts of many radios, there's a little LCD, just like the ones on the computers. They're small, and they show the frequency and they show everything else, and you see a picture of a meter that looks like that. Here's a representation of battery, a single cell battery, a multi-cell battery, and plus is the longer of the leads and minus is the smaller, as you can see here, whether it be a single cell or multi-cell. Schematic diagrams. That's the symbols that indicate each type of component. Typically, many times, in this particular case, they've got resistor number 66, 383K, that would be 1,000 ohms. Remember from our first K stands for kilo ohms, which would be 1,000 ohms. Many cases, the schematics are so tightly drawn that you don't have room to have the actual value, so you actually have to go to a chart over here somewhere to see what R66 is or R53 or to see what this particular transistor is or diode or whatever. So again, they give them different things. That, like I say, this particular one is easier because it's simple enough that they can put the component values right at the component. This is something you will do on the test. You will have to identify different components on the schematic diagram. Now, this talks about the lines between the parts indicate the connections. So in this particular case, they show connection. In this particular style, they have a dot where they're actually connected. Let's see if I can find one where they don't connect. But anyway, if they didn't have a dot, it's not connected. Okay, let's review. We talked about impedance. So what is impedance? Opposition to flow of AC current. That's right. It's like a resistance, yeah. But just so we don't mix up impedance and resistance, we just say opposition of flow to an AC in a alternating current. What is the unit of impedance? The ohm, just like resistance. What is used along with an inductor to make a tuned circuit? A capacitor, that's right. What is the example of a tuned circuit? In this particular case, the answer they're looking for is L and C, that means inductor and capacitance, in series or parallel to form a filter. Again, we showed you can have them in series or in parallel. And so the answer to this question, tuned circuit, is an inductor and a capacitor, L and C, in series or parallel to form a filter. What class of electrical components is capable of using a voltage signal to control the current flow? Transistors, that's right. Remember, a little current or voltage can control a big current. What electrical component allows current flow in only one direction? Diode, that's right. What kind of component can be used as an electronic switch or amplifier? Transistor, that's right. What kind of component can be made of 3 layers of a semiconductor material? If you remember, the transistors had 3, PNP or NPN. So 3 layers of a semiconductor material make a transistor. That's the answer there. What kind of component can amplify a signal? Transistor. How is the cathode end of a diode usually identified? With a stripe. Usually they have a stripe on the stripe on the diode. Well, here's the easy one. What does LED stand for? Light emitting diode. And what does FET stand for? Field effect transistor. Field effect transistor. What are the names of the 2 electrodes of a diode? Cathode and anode, that's right. What are the 3 electrodes of a PNP or NPN transistor? Base, emitter, and collector. Now, what are the 3 electrodes of a field effect transistor? It's called the gate, the source, and the drain. Gate, source, and drain. What is the term that describes a transistor's ability to amplify a signal?
Gain.
Gain, that's right. How much gain do you get with a transistor? What converts alternating current into varying direct current? A rectifier. What component is often used as a visual indicator? Okay, a LED, light emitting diode. We talked about they taking the place of these guys. Okay, what is the name of the device that combines several semiconductors or other components into one package? Integrated circuit, or IC, that's right. Okay, in this particular circuit, the one that you see on the board, what is the purpose of component number 2? So what is component number 2? It's the transistor. So what does it do? What can you use a little current to do? Control the flow of a big current. So you're controlling the flow of current with this particular transistor. Again, remember, you can have a little current control a big current, or a little voltage control a big voltage, depending on which type of transistor you have. That's particular BJT, so that would be a little current controlling a big current. But essentially, what you remember is it controls the flow of current. Okay, what electrical component is used to connect or disconnect electrical circuits? A switch. What electrical component is used to protect other circuit components from current overload?
Fuse.
A fuse. What best describes a relay? Now they'll have 4 there. It's a switch controlled by electromagnet. Remember, we talked about the coil, and then that essentially, when it's energized, causes the switch. Can cause it to be open or closed. If you can have a normally open relay or a normally closed relay, but essentially it's a switch controlled by electromagnet. Okay, component number 3. What kind of switch does that represent?
It's a single pole, single row.
That's right, single pole, single throw. Which of the following can you use to display a signal strength on a pneumatic scale?
Meter.
A meter, that's right. What is the purpose of a fuse in an electrical circuit? Yes, the official answer is to interrupt power in case of overload. Why is it unwise to install a 20 ampere fuse in place of a 5 ampere fuse?
Because you can burn out with your circuit.
That's right. Essentially, you put a 5 amp fuse in there because you said, the designer said, anything more than 5 amps may damage the circuit. Well, if you got a 20 amp fuse, it's going to happily pass right up to 20 amps. And your designer of that particular radio said, you can hurt it if you have more than 5. So that would not. So essentially, the official answer is excessive current could cause a fire. What is the name for standardized representation of components in an electrical wiring diagram? Schematic, that's right. Schematic symbols is the full name. Okay, what is component number 1 here? A resistor. What is component number 2? Transistor. What is component number 4? Yes, a battery. I think I jumped over number 3 today. What is component number 3? The lamp, right. Okay, now on the next diagram, what is component number 6? Okay. What is component number 8? LED. Again, we didn't mention that specifically, but you see it's a diode, but this shows, essentially indicates the light coming out of it. What is component number 9?
Variable resistor.
A variable resistor, that's right. And then what is component number 4? Transformer, that's right. All right, in this diagram, what is number 3?
Variable inductor.
A variable inductor, that's right. What is component number 4? We haven't covered that, but that's an antenna. That's a schematic for an antenna. What do these symbols on an electronic circuit schematic diagram represent? Electrical components.
Yeah.
What is accurately represented in an electrical circuit diagram, schematic diagram?
Connections of the components.
Is the way the components are connected. It is not the way they're laid out on the circuit board or on the chassis or whatever. It's just electrically how they're connected together. So you need to be aware of that. Oscillators are comprised of an amplifier with feedback to produce a sine wave at a single frequency. So you've got an amplifier. Now an amplifier, this is a block diagram. This is not a schematic diagram because it doesn't show the transistors or chips or whatnot. It just shows this is an amplifier. If you wanted to see a schematic for that, that would be somewhere else. But essentially, it uses feedback to produce a pure sine wave. And almost everybody here has heard what uninterrupted feedback is like. That's where you have a person with a microphone and you get feedback from the speaker to the microphone. So oscillators do the same thing, but they're doing it in a controlled and carefully designed method. So they produce oscillation at a certain frequency, that is one that is chosen by the person running the radio. Okay, this is a simple CW transmitter block diagram. For those of you who weren't here last week, CW stands for continuous wave. That's really what we call Morse code, what you would call Morse code. Essentially, it's a continuous wave. We're turning it on and off to create letters and numbers and symbols, etc., to transmit information. So you have an oscillator that's set up at the milliwatt level. You see the MW there. So it's making just very, very low power frequency. Then we've got a driver. The driver bumps it up to a few watts. And then we turn the driver on and off. And we've got a power amplifier that gets us up to 100 watts, then goes out to the antenna. So by turning, we're making a tone, and by turning that tone on and off, we can transmit information through Morse code. It actually can be more simple than Morse code. If you were talking to somebody that you knew, one beep could mean yes and two beeps could mean no. Okay, filters. As you will see, and we covered this last week too, when we have an oscillator, remember it's generating a frequency. But for those of you here last week, what happens when we generate a frequency? We also create harmonics. 2 times the frequency, 3 times the frequency, etc. Well, here we only want one frequency to be amplified to a few watts and then amplified to 100 watts. We don't want all the harmonics to be amplified. And the harmonics are naturally not as strong as the principal or primary frequency. But still, they can be strong enough if the principal frequency is at 100 watts, they might be at 5 watts. But 5 watts, you can communicate around the world on 5 watts. So you don't want that to happen. So what you do is you come up with filters among other things, filter out the frequencies that you don't want and pass through the frequency that you want. And this particular one shows since a harmonic is a multiple of the fundamental frequency, so if you have a frequency at, we say 3.5 megahertz, which is the bottom of the 80 meter band, it'll automatically do one at 7, at 10.5, at 14. Now something you might notice if you started memorizing your frequencies is that this is a ham band, this is a ham band, and this is a ham band. They initially did that, remember this was back in the 20s and 30s, because they knew harmonics would occur. People were building their own transmitters, and at the very least, the second harmonic and the fourth harmonic here are essentially within the ham band. So if we were disturbing anybody, we were just disturbing other ham. So that was considered not as important, although it doesn't mean we're supposed to do that. But what we really want to do is not put out anything of any substance on these other frequencies. When we send out the signal at 3.5, we want it to be just 3.5. So what you can do here, all these other frequencies, the harmonics are at higher frequencies, so you create a high-pass filter, a low-pass filter. So anything below this passes this cutoff frequency, and anything above it is attenuated, or essentially it's cut down. Now you see it doesn't go 100% to zero. A filter is not perfect. Lots of things you'll see drawn with squared off like this. Well, that can occur, but it doesn't occur naturally. Normally what you get, rather than it's not just is you get slopes here. And it's what you have is how much attenuation occurs at so many frequencies away from, or so many kilohertz away from the cutoff frequency. So anyway, that's one of the things we talk about, capacitors and inductors, and that's one of the things we do. We make a low pass filter that would pass the 3.5 megahertz and attenuate anything above that. We can have a situation with a high pass filter where we have for some reason lower frequencies. Maybe we're using a frequency multiplier, which is used in many radios, and so we multiply the frequency on purpose. We want to pass the higher frequency and stop the lower frequency. So again, you can create filters that are low pass or high pass, or you can create filters that are band pass filters, where they will pass anything essentially between these two red lines here, or orange lines, I guess they are, and attenuate or try to stop anything on the outside of that. So remember, we want to make sure that our signal is only of a certain bandwidth, so a band pass filter can help us with that. And the way that works, where it works practically speaking, as we talked about, let's say this is 3.8 megahertz, 3.9, and 4.0, 80 meters. Okay, your signal is actually about how wide is a single sideband signal? We had that last week. Anybody remember the number? 3 kilohertz. So your signal is maybe that big. So let's expand that. And so your signal is this big. Okay. Well, somebody else talking, and remember, really, it's like that. It's not a straight line. Somebody else is talking next to you with a 3 kilohertz signal, and theirs kind of overlaps yours a little bit. So what this does is that band pass filter in a receiver allows you to scope in on the signal you want to hear and filter out most of, hopefully all, of the signal you don't want to hear. So that's partially why you have band pass filters. Now, a notch filter does a different animal, and that is, let's see what we got here. We've got our 3 kilohertz signal here. What did we say a CW signal is typically? This is 3 kilohertz. A CW signal is typically like 500 hertz, or half of 500, 0.5 kilohertz. So if some bad person, through either negligence or being a jerk, decides to tune up in the middle of where you're talking, you've got a little signal interfering with your big signal. If we could just take that little signal out or attenuate it, then we would be able to communicate better with whoever we're trying to talk to. Well, that's what a notch filter does. It stops one little signal, it passes everything there. So in this particular case, it would pass, say, 3 kilohertz or better, which is your single sideband signal. But if you have a CW signal that's 500 hertz wide, you can notch that out. And essentially, again, none of this works perfectly. It's not going to totally remove that signal, but it will make it so weak that it's not so invasive to you. It doesn't cause you to cease to be able to communicate with the person you're talking with. So that's why you have such a thing as a notch filter. So we have band pass filters and notch filters. As you can see, filters are extremely important in radio. You have tons of filters in radios that you use every day, your AM, FM type radios, and you don't even know it. They're switched in automatically. But in ham radio, because we do specialized communication, we in many cases need the ability to switch in and out specific filters to accomplish whatever communications goal we're trying to do at the moment. So that gives you a sense of what we use filters for. Modulator. A modulator changes the amplitude, frequency, or phase of an RF signal to convey information. Well, again, the simplest being CW, or Morse code, you change the amplitude from 100% to 0% to 100% to 0%, on and off, to make code. Da being A, da did it B, etc. So, but we can also modulate with voice. We can even modulate with television signals, etc. So you have an unmodulated RF carrier that the radio makes. Then we have a modulating signal, voice, video, or data, and they're combined in the modulator. And remember, that's another thing. That's another case of the transistor using a small signal. The modulating signal in many cases is a small signal, 0 to so many nanovolts or microvolts, and then this converts it into a larger signal, which creates your modulated carrier, which can then go on and be amplified and to the point where you can send it out and somebody can actually hear you. So once again, that shows you where transistors are used in making this happen. The block diagram doesn't show it, but the schematic that would show exactly that. Transistors or integrated circuits with transistors on them doing that particular job. A mixer combines two RF signals to produce a useful frequency shift of the signal at its output. So you have the RF signal at a certain frequency, then you have an oscillator putting out a second frequency. They mix. And remember, we get two output signals. One is plus the two frequencies plus each other. One is the higher frequency minus the lower frequency. So you've got two different signals. How do we choose one of those signals? A filter. So we've got two signals here now. We filter them and then amplify them, and we choose whichever one is that we need at the moment. So that's where you get, in radios you'll see an IF, intermediate frequency, and that's where you use mixers and whatnot to create your final frequency. But when you're dealing with your intermediate frequency, it's the frequencies that take place in mixers or the initial frequency or whatever in creating the signal. Okay, a direct conversion receiver. It takes a modulated signal directly. We filter the signal to get the exact frequency we want. Then we put it into a mixer with a local amplifier or a local oscillator, then into the amplifier, and then we've got now something that's strong enough to drive a speaker or headphones. And this is about the simplest kind of receiver that you can have. There's reasons why you say, well, if it's the simplest and it works, why don't everybody use it? Well, there's disadvantages to it, some things that it won't do as well. But that's the basic direct conversion receiver, and that particular receiver can be put on a single chip. So sometimes you see one chip receiver, and typically they're direct conversion receivers on a single chip. Okay, super heterodyne receiver. Made by a man named Edwin Armstrong, invented by him. And Edwin Armstrong is one of the names you may not be familiar with, but one of the, again, foundational people of ham radio or radio in general. He had some epic battles with Sarnoff with RCA, and unfortunately he won the battles he won the war, but he lost some of the battles. But anyway, he created super heterodyne receiver, among other things. This was in the 20s and 30s, and what it could do that most of the other ones couldn't do, there was something called a regenerative receiver, which they still have today. But it has sensitivity, that's the ability to hear weak signals. Selectivity, again, that's where you've got signals all around, but you want to concentrate on just one signal. So to be able to differentiate the signal you want to hear in the presence of strong nearby signals. And in this particular block diagram, you have a preamplifier which increases the sensitivity, so you can hear weaker signals. Then you've got a mixer with an oscillator, a filter. I mentioned IF amplifier, intermediate frequency amplifier. Then it comes into a demodulator that takes the signal that you're hearing and actually demodulates the variable carrier through either single sideband or AM or FM or whatever, but for this particular purpose it was AM. Sends that to the audio amplifier and then out the speaker. So it processes all the signals at one frequency. That's what the mixer does. Essentially, you can optimize all this circuitry because the mixer takes the signal that you get, that you tuned into from outside, filters it, and it essentially deals with it all at one frequency. So you can optimize the circuits for that frequency, and that increases both the sensitivity and the selectivity. So that's the block diagram of a super heterodyne receiver. And again, it kind of revolutionized radio of its era. And still, most of the radios you get, if you get a shortwave receiver or whatever, is a super heterodyne receiver. Transverse. Used to more so than now, but still even today, it is for the same power and same aspects, a high frequency or very high frequency or ultra high frequency transceiver is more expensive than an HF type transceiver. Now, they don't seem that way if you just get one tune for a single mount. A little 2-meter radio is cheaper than an HF radio, but the HF radio, remember, is going to cover a huge range of frequencies. So that's what makes it seem. But anyway, so something that some people do under some circumstances to reduce the expense is they use an HF rig operating, say, at 10 meters, typically 10. And you have an up converter, in this case, to go to 220 megahertz. And so you take a 10-meter signal, 10 meters going from 28 megahertz to 28.15, and it swings it to 222 megahertz to 222.15. So that essentially up converts the transmitter, and then when you're listening, it converts down the 220 megahertz signal down to 10 meters for you to be able to listen to it on an HF rig. And that, in some cases, is a less expensive way to do it than having a dedicated 220 megahertz radio. So that's why, one of the reasons you have transmitters. Okay, let's see what we got here from the questions. What is probably happening, so this actually gets back to something we talked about a couple of times ago. What is probably happening when an ohm meter is connected across an unpowered circuit, so it's unpowered, and it initially indicates a low resistance and then shows an increasing resistance with time. A capacitor, that's right. You've got generally a large capacitor in there, and that capacitor discharges, and while it's discharging, it's very low resistance. Once it has completely discharged, it's almost an open circuit, so it's very, very high resistance. What kind of circuit is used to convert a radio signal from one frequency to another? We showed several of them. A mixer, where you mix two different frequencies, and then you come out, you actually have two other frequencies, the addition and subtraction of the two frequencies, the plus and the minus, but then you filter that to get whatever you want. But the kind of circuit that's used to convert a radio signal from one frequency to another is a mixer. What's the name of the circuit that generates a signal at a desired frequency? That's right, oscillator. Oscillator is what you initially use to charge, essentially specify the frequency you want to operate on. What do we call combining speech with an RF carrier signal? Modulation, that's right. Okay, what term describes the ability of a receiver to detect the presence of a signal? What term describes the ability of a receiver to detect the presence of a signal? What characteristic do we need in it? Sensitivity. You're just detecting a signal. At this point, we're not worried about choosing a signal. It's just, can we detect any signal? What determines the ability of a receiver to discriminate between multiple signals? Selectivity, that's right. What device will take the output of a low-powered 28 megahertz single sideband exciter and produce a 222 megahertz output signal? Transfer, that's right. Where is an RF preamplifier installed? RF is radio frequency between the antenna and the receiver. Many times they're built into the receiver. In some cases, you can buy an external preamplifier that goes between the antenna and the receiver to amplify the signal. Okay, chapter 4. We've covered some pretty heavy stuff if you're haven't been into electronics. Now it'll be a little easier, and this is the kind of stuff I've mentioned to you. Many things that we cover on the test are things that you would need to know about if somebody gave you a license. If the president or the head of the FCC said you've been an exemplary person and we will give you a ham radio license, you would still need to know things to get on the air and whatnot. And this is some of the things that you would need to know, is how propagation antennas and feed lines all work. So this is not quite as heavy electronically as what we've been covering, but still some very important things to know about. Okay, radio radio waves travel from the antenna in straight lines. They also become weaker with increasing distance from the antenna. And the radio horizon is the distance by which two stations can communicate by a direct path. Now, what we will see, and if you've read in the book or whatever, you think about the radio horizon being what you can see, which might be 15 miles away. Well, actually, the Earth is not quite as curved to a radio wave as it is to light waves. So radio waves will cover the curvature of the Earth a little more, so the radio horizon is a little beyond the visual horizon, which actually is very convenient that it is. Okay, we get the antenna, and UHF, VHF signals propagate slightly beyond the visual line of sight, which we talked about. One thing that can happen at what's called sharp edge diffraction is it comes here, and actually you can backfill with radio here, radio waves here. Refraction is its ability to follow the Earth slightly. This is what's called knife edge propagation. The ground wave is not what we will talk to you on if we talk to you, because the ground wave is at HF and lower frequencies follows the curvature of the Earth. But remember, it gets weaker the further away it gets. So with our power, we'll be using 100 watts, and I guess your radio, that radio would be 100 watts. So with just pure ground wave, it would be attenuated between Boone and Raleigh. So we wouldn't be able to talk that way. We've got to bounce the signals off the ionosphere in order to do that. We'll talk about the ionosphere in just a minute. First, though, something that came up, a lot of people heard about it for the first time after 9/11, the attack in 2001, is the fact that in many cases the firefighters' radios did not work well in the building. Well, in some cases, as we say here, this room is a terrible room to use for a radio, even for 2 meters, because we're in the middle of a very big building. The building has a metal roof. It may be built up beyond that, but almost certainly metal there. So this is a hard room to get a radio signal into and out of. But even radio signals in places where there are windows, you mainly get penetration through an opening that's at least half a wavelength on the side. Now we say mainly. It's not 100%, but the primary propagation is if it's a half a wavelength on the side. So then UHF, the shorter wavelengths, work better than the longer wavelengths because you're more likely to have an opening that the signal can get out of. There wouldn't be propagation through the small opening. Now, there's something called a Faraday cage. A Faraday cage is a structure you build, can be little or large, that essentially no radio waves can get in or out of. And some people build them, some preppers build them to put radios in case there's an electromagnetic pulse or whatever, naturally or unnaturally, to protect the radios. Your house, though, is not a Faraday cage. Again, even a building. Some radio waves can make it through despite this, but this is one thing that if you're trying to make your communications within a building work as well as possible, then you'd like to have UHF because you're more likely to get better propagation through these openings that are at least a half wavelength on the side. Yes?
Does the polarization of the wave affect which orientation the opening do?
Yes, it would help if the orientation, if it was like a vertical window with a horizontal, with vertically polarized. But that's not a huge thing. It's has some importance, but it wouldn't be huge. Mainly it would be just big enough for the wavelength to pass through. Okay, something else you can have. And this is a good little diagram and graphic, but it's wrong. It actually shows something wrong. Multipath is where the radio wave is reflected through the ground. You got a direct wave here, you got a reflection off a building, and then they all get to the antenna. What is wrong here is that they're all arriving at the same time. In reality, the speed of a radio wave is approximately the speed of light, And in essence, this has to travel further. So in reality, this guy's traveling much faster than this guy. But your radio wave won't do that. Your radio wave in each direction is going to be at the same speed. So this is going to get here at one time, this is going to get here at another time, and this will get here at another time. And that causes problems, can cause problems. It can cause what's called mobile flutter. Picket fencing is where you always, when I talk like I'm doing this, and you can hear part of it and you can't hear part of it. That's something that's called picket fencing. It causes an increased error rate for digital data. So multipath can cause a lot of problems. In some cases, if you move just a few feet, if you've got a handheld or even if you've got a car, if you can just move a few feet, you'll find the reception and communication will be much better, because then suddenly we're not bouncing off this building anymore, and maybe the ground reflection is not quite as severe in the new position. So I will mention that is something that's on the test. And that's something you also might need to use in your own career as a ham. And that is, you're talking to somebody on your handheld, you're talking in the car, they can't quite hear you. In some cases, moving just a little bit can make a big difference in how well you can communicate. Tropo propagation. Temperature inversions can bend UHF and VHF signals. Something called ducting is possible, can cause UHF-VHF communications over 300 miles. I have experienced this a number of times. Actually, fall and spring are some of the best times to experience it. You probably have experienced, if you've got an FM radio, maybe you've tuned across the band and you've heard some signals that you don't normally hear. Actually, a little bit of that was happening this morning when I was getting ready to come here. And I used to do work, when I worked for the Department of Energy, I did work at UNC Charlotte. We had some research going on there, and I would drive to UNC Charlotte, and I'd be there early in the morning, and I could hear the Raleigh repeaters. Normally, you do not hear Raleigh repeaters in Charlotte, but I could hear the Raleigh repeaters, and so that was temperature inversions and ducting that was causing some of those type phenomena. Again, I could hear the Raleigh repeaters, I could talk to somebody, but then literally an hour later, nothing. So they are generally short-term phenomena. Ionosphere, that's something we depend on a lot for HF communications. Because we talk about line of sight, even the radio horizon, a ground wave, that only gets us so far. That gets us 100 miles, maybe with ducting 200 miles, except you don't get ducting on HF. But if we want to talk around the world, we need some way to do that. And fortunately, we have the ionosphere. It's ionized gas that's around this planet. It's essentially a circle around the planet. Energy comes from ultraviolet and X-rays emitted by the sun, and it's from 30 to 300 miles. And the International Space Station is actually about 220 miles, so it actually is orbiting in the ionosphere. So something that generally would mean is that we should be able to talk to it on HF. Now what happens is UHF will go straight through the ionosphere. That's good and bad. It's good because we can talk to our satellites and talk to the moon and send satellites to Saturn and whatnot and get signals to them. It's bad because they don't bounce, so we can't talk around the world on UHF, VHF. But that's why, it's a great thing about having different frequencies. Some frequencies do, some don't. So here we have the ionosphere. You've got where the troposphere or stratosphere from 30 to about 60 miles, you've got what's called the D layer, 60 to 70, the FE layer, and in the 100 mile to 300 mile range, you've got the F layer. Now, first of all, these numbers are not hard. That's approximately where they are, and they shift. This F layer can shift lower, can go higher. It bounces all around. This is not a hard piece of material out there. This is a radio wave ionization layer, and again, its ability to reflect, where it tends to reflect, etc., changes all the time. That's what makes things interesting. It makes it tough if I absolutely have to talk to somebody in Nigeria this afternoon. maybe the ionosphere works well to do that, maybe not. That's one of the reasons satellites have replaced that for a lot of things where you absolutely must talk to them. But maybe it does work, and in that case, we require a lot less hardware than the satellites do. But anyway, so this is what happens. You've got the different ionospheric layers, and we'll talk about how the different ones tend to work. Okay, what you get is not reflection when we talk about bouncing off the ionosphere. It's called refraction. You can get more refraction that can cause it to come down faster. You can get less refraction. Typically, more refraction is from more ionization, or if you're using a lower frequency, it produces a shorter hop. Less reflection is from less ionization or a higher frequency, and it produces a longer hop. Which is good? Which is better? Depends. If you want to talk to somebody here, this is better. If you want to talk to somebody here, this is better. So in reality, that's where you can choose the frequency, depending on which frequencies are hopping where, and have a better chance of talking to somebody farther away or a better chance of talking to somebody a little closer. Ground reflection, it means we can have multiple hops. We can have, essentially, you refract off of the ionosphere, it reflects, and you can get multiple hops, which gets you even further and further around the world. We talk about the D layer. Well, the D layer, the ionosphere, the ionosphere gives and the ionosphere takes away. The D layer can absorb different frequencies. In this particular case, it will almost always absorb in the 3 megahertz range. That would be 80 meters. 5 megahertz up into 7 megahertz, which would be 40 meters. That area, some of it can get through, but it winds up being attenuated somewhat. Then at, say, 40 meters, 7 megahertz, it may be able to go through without being attenuated at all. And again, that varies. Whatever the attenuation is right now, it will be different at 3 o'clock this afternoon. And it'll be different at 8 o'clock tonight, or 7:30 tonight. So that's where you get different D-layer absorption, and that can that can cause you not to be able to talk to somebody you want to talk to. I didn't mention the D-layer pretty much goes away at night, so you don't have to have that absorption, which is why radio signals tend to go further at night than they do during the day. You don't have that absorption. But what it also means, it's one of the reasons why 7 megahertz, 40 meters, is one of the best round-the-clock bands because it is least affected by all these attenuations and various things that can happen. 20 meters, 14 megahertz is kind of similar. It's usually pretty good day or night, but it can go down at night. Like I say, 40 meters generally is pretty good to 7 megahertz is usually pretty good day or night. So that's why a lot of communications like that take place on 40 meters or 7 megahertz. Okay, we talked about how the military determines what frequency they want to operate on. Well, this is kind of what we do to determine what frequency we want to operate on. We have 2 different frequencies that, again, they're always changing, but we try to know about where they are. One's MUF, which is maximum usable frequency, and the other is LUF, which is lowest usable frequency. Above the MUF, the signals just go straight out into space. So 2 meters is almost never the maximum usable frequency because almost always 2 meters will go straight out into space. That's good. We can bounce signals off the moon. If they were attenuated or didn't go through the ionosphere, we would be able to do that. But it means that international communication through refraction and through the ionosphere is not really possible on 2 meters. Between the maximum usable frequency and the lowest usable frequency, the band is open. So essentially that's when you can talk long ways away. Sunspots increase the maximum usable frequency. That's why we're always interested in sunspots. We've had a pretty rough 11 or 12 years recently. We've had lower sunspots than, in fact, we've had some historically low. You have to understand when we talk about historically low, kind of like the climate and everything else. were dealing at best for 300 or 400 years. Before that, they did some determination of what sunspots are, but we didn't have the scientific instrumentation and whatnot. So it's historic within the time that we have good data, which even if you want to stretch it, probably not more than about 1,000 years. But anyway, so it's historic for that. For whatever reason, we're not quite having as many sunspots as we have. When there's lots of sunspot, 10 meters can be open all through the daylight hours. You can contact worldwide with just a few watts on 10 meters. That's important to you because one of your frequencies that you can operate on is 10 meters. As a technician, the only HF band you can operate on with voice is 10 meters. Now you can operate on Morse code on all of what we used to call the novice frequencies if you want to learn code. Again, you don't have to learn code to get your license, but you can operate on those frequencies. But if you want to operate voice, your only HF band is 10 meters. So you'll be rooting for sunspots yourself. Of course, we'll be rooting for you to upgrade to extra, I mean to general at least, then you can get all the bands. But anyway, also, a 6 meter F-layer propagation can be possible if the sunspots are right. 6 meters, some people call it the magic band because really unusual things can happen on 6 meters. That, I mean, it can be dead or you can work halfway around the world. So it's really unusual and very interesting band to operate on if you decide. And you do get pretty much full 6 meter capability as a technician. Again, something else we hadn't mentioned, but multipath, you can have that problem with bouncing off of the ionosphere and even refracting. You can have multipath for that. So multipath is something that can occur on both the UHF and VHF and HF frequencies. Sporadic E. You can get a highly ionized patch in the E region that can reflect 10 meters, 6 meters, or 2 meters at certain times. But it's called sporadic because you don't ever know when it's going to happen. The people that are really into that have a radio tuned to some of these frequencies just about round the clock. There's something called beacons, and that is people who have a radio that's running about 1 watt. I don't remember what the rule is. It's got to be pretty low power. But they're running, people in California are running a 10 meter beacon that's a radio signal right now. They run it essentially 24 hours a day. So you know that person's in California, you know the frequency of their beacon, you try to tune it in on your radio. If you tune it in, that means you pretty much can talk to California. If you can't tune it in, probably not. So similarly, there's beacons in other places in the United States, and there's lists of those on the internet. So one thing they accuse 10 meters of, or even 6 meters as well, people will turn on the radio, they don't hear anything, and they think, well, the band's dead. In many cases, if you just call CQ, you give out a call saying, I want to talk to somebody will hear you. So it's not dead, it's just nobody's using it. But the beacons help with that because there's always a transmitted signal from them. And maybe there's one in Iowa, and you hear the one in Iowa, and you know we've got whatever kind of propagation. We've got some propagation from here to Iowa, and maybe I can talk to them. So, but one of the ways you can with 6, 10, and 2 meters is what's called sporadic E propagation. So again, it's something relatively rare, but that does occur. The aurora is ionized particles that can get pulled to the poles, the North Pole and the South Pole. And it can cause rapid changes in signal strength. But it also can affect propagation because it's ionized parts of the atmosphere, and as we see, that can cause reflections and whatnot for radio waves. Meteor scatter. Meteor trails are ionized. They reflect 6 meter signals well and also 2 meter signals in some cases. You can communicate up to 1,500 miles if the situation is right. However, you got to be quick because it lasts for several seconds, but it doesn't last much longer than that. So there's specialized ways of trying to communicate during meteor scatter. Try to get your burst of, many of them are digital modes. You get your burst of information in, somebody else gives you their personal information, sometimes it's CW. But there is such a thing on the meteor showers that you hear about. A lot of hands are interested in that to see if they can operate some meteor scatter radio. Okay, what do you do if another operator reports that your 2 meter signals were strong just a moment ago, but now they're weak or distorted? Yeah, you might move a few feet. Y'all might also change the direction of your antenna if you have a possibility of doing that. You have like a beam antenna, but at the very least try moving a few feet, as we discussed, and it might be a lot better. Why are UHF signals often more effective from inside buildings than VHF signals? They can more easily penetrate small openings like windows. So it says the shorter wavelength allows them to more easily penetrate the structure of buildings. What term is commonly used to describe the rapid fluttering sound sometimes heard from mobile stations that are moving while transmitting? Picket fencing, that's right. What is the likely cause of irregular fading of signals received by ionospheric reflection? You got irregular fading. That's combining signals through different paths, the random combining of signals. Like I say, sometimes they might get there exactly the same time, and that's great. That reinforces it, but sometimes they might get there at different times, and it causes irregular fading. You don't know what, you can't tell exactly what's going on. What may occur if data signals propagate over multiple paths? We talked about that briefly. What happens to anything? Yeah, you get error rate. Your error rate's likely to increase. Just like, to be honest, if I'm listening to you talk and I can't quite understand you, that's a high error rate. We don't think of it that way, but that's the same thing with computer data. If the signal's fluctuating, then the error rate is going to increase. Which of the following effects might cause radio signals to be heard despite obstructions between the transmitting and receiving stations? Knife edge diffraction, that's right. Think of the mountain that was showed the picture of, very sharp. What mode is responsible for allowing over-the-horizon UHF, VHF communication to ranges of approximately 300 miles on a regular basis? Their answer is tropospheric scatter, which is part of what ducting is involved with. What caused tropospheric ducting? Temperature inversions. Temperature inversions. What is the radio horizon? It's the distance. The radio horizon is the distance. How far away can I talk to you by direct path? And remember, it's more than the visual horizon. It's further away than that. But it's the distance over which two stations can communicate by the direct path. Well, what we're going to discuss now is decibels. And I have a secret weapon to help you with the decibel question. Decibels are commonly used in the description of antenna characteristics. It's a way of comparing two different powers. Essentially, one of the big things that you say is this antenna, and we'll get into beam antennas a little bit, but this antenna has X amount of gain over another antenna. And that's essentially a fraction based upon the ratio of the two numbers, or it's not a fraction, but it's a number based on the ratio of two numbers. And it, so for instance, a dipole, which we've seen and we'll see more again, has about a 2.1 dB gain over what's called an isotropic source. So dBi means dB over isotropic source. So The point, we'll get to that a little later too, isotropic source doesn't actually exist. It's a electrical engineering construct for something that would be like a perfect antenna at one point. But anyway, you're comparing two different things. So if somebody just tells you, and you'll see this all the time, this antenna has 8 dB gain, that's generally not worth a whole lot. Because what they should be saying is 8 dBd. You've got to have a reference. Is it's dB compared to what? And the general thing to remember, decibels are logarithmic powers. And so in reality, 3 dB is the doubling of power. So if you double your power, you've got a 3 dB gain. 6 dB is quadrupling of the power. 10 dB is a 10 times change in power. And if you're decreasing the power, or you're losing signal, then halving the power is minus 3 dB. 0 dB is no gain or minus. So 3 dB is, so we're talking about with this dB over an isotropic source, not quite doubling the power. Of course, again, there's no such thing as an isotropic source, so in reality, that's why most of the time you compare it to a dipole. A dipole is a real antenna, and we can build a dipole, and we'll talk about that a little later, and we can use a dipole, so it's important to us, or can be interesting to us to know how much gain do we get compared to a dipole, a simple dipole. Well, the secret here is we could spend an hour or two talking about logarithms and decibels and all that, but the fact is you only have about 3 questions you're going to be asked. So if we memorize those 3 questions, then you've got dB covered. Antenna fundamentals, and we're going to get into dipoles and other types of antennas. Antenna, first of all, is one of the most important things in your radio station. We all like to have pictures of our radio room, radio shack, whatever you call it, and stacks of radios and all this kind of stuff, and the latest radio with the best little screen on it and everything, and all that's great, that's fun, and I like it too. But generally speaking, if you've got the best antenna, if you've got a top 10% antenna and a middle range radio, you'll do much better than if you have a top 10% radio and a middle range or worse antenna. So anyway, it converts radio waves to voltage for the receiver, or then it converts voltage to radio waves if you're using a transmitter. The feed line is what connects the antenna to the transceiver or transmitter. The antenna has an impedance called Z at the feed point that depends on the frequency of the signal and the dimensions of the antenna. Remember, this feed point Z is just resistance. It has no reactance. Actually, there's some situations under which you can have reactance. You don't want that, but it can. But typically, you want the feed point to be pure resistance. Okay, in an antenna, the elements do the radiating. They're the cross pieces. You can think of it also, although we're all getting, or some of us are getting a little old. I could say a TV antenna, but a lot of people say, what's a TV antenna? So, anyway, that's right. But anyway, a TV antenna, if you've ever seen one of those, are these kind of antennas used for AM or FM radio or whatever. An array is multi-element antennas. This is an array. Driven array is where all the elements are connected to the feed line. In this particular case, it's a driven array of 14 elements. All these elements are connected to the feed line. Most Ham beams are not driven arrays, they're parasitic arrays, where some elements are connected to the feed line and some are not. And the parasitic elements are the elements that are not connected to the feed line. We'll discuss how that works in a little bit. Okay, this is a very common type ham radio antenna, like a strap. But anyway, there's several brands that look very similar to this. This is a 3-element parasitic array, what we call a beam. The driven element here is the first element, the middle element that is the driven element. The reflector is the back part. It is about 5% longer than the driven element. And the director is the front element. It's about 5% shorter. If you see one, not the one we were looking at, but if you see one that has many elements on it, which you will see a lot of times for 2 meters, and you've got one that has almost 100% of the time, the driven element is the next to the back one. There is one reflector, and the rest of these are all directors. That's just the way the parasitic antenna design works. So you feed the dipole, which this is actually a dipole that you feed, is the next to the last element. Again, these directors get correspondingly shorter the further you get away, about 5% or a little less each time. But the second one is the actual driven element. The rest are all parasitic, but you don't have multiple reflectors. The only time you have multiple reflectors, and I had a picture and lost it, and so I'll have to see if I can get it back, is occasionally, if we look at an antenna in 3 dimensions, we got the antenna like this. We've got the once in a while, this is the driven element. Once in a while, they'll have a little post here and another reflector above and another reflector below. In the reflector, you never see that with HF antennas like that, but occasionally you will see them on UHF, like a 2-meter antenna or a 440 megahertz antenna. They're pretty rare. I have never really done a great deal of research into them. I think they're pretty rare because I think this helps a little, but not as much as it costs to actually do it.
I'd say UHF, TV antennas.
Yeah, there's TV antennas like that. There's a few ham radio 2-meter antennas like that. But essentially, most of the time, you've got one reflector, one driven element, and then a bunch of directors, which creates your parasitic array. Okay, your radio waves can have both a magnetic field and an electrical field. In this particular case, the vertical is the electrical field, the horizontal is the magnetic field. So since the vertical is the electrical field, then this is a vertically polarized electromagnetic wave. And this particular shows the direction of travel. Polarization, that's the orientation of the antenna's electrical field. You can tell that polarization in UHF, VHF makes a difference because if you have your handheld and you're listening like this and you turn your handheld sideways, you will notice the signal strength dropping. I've done that many times. That's why if you look at TV and somebody's holding it sideways, I guess they think it looks cool or something. But that's not the way to go. If you want the maximum range, you want your antenna vertically on UHF and VHF because that's what typical polarization is for UHF, VHF. So in line of sight situations like UHF, VHF, the polarization makes a substantial difference. So you want to be sure that your polarization, it doesn't mean you absolutely cannot communicate. It just weakens the signal substantially. So it's not that it's totally impossible. It's just it weakens the signal. So cross polarization, if you're trying to do that, that causes losses in the signal. In HF, it's not as critical because the ionosphere, as it's bouncing around off the ionosphere, it kind of changes polarization anyway. So elliptical polarization is a combination of vertical and horizontal, and that's really what you kind of wind up with after it bounces off the ionosphere. Here's a horizontal antenna. The elements are essentially parallel to the ground. Here's a vertical antenna. The element is essentially perpendicular to the ground. So it makes it easy to remember that. Antenna gain. You can direct the energy in a certain direction. Just like, as we'll see in a minute, actually, I don't have the pictures but like a flashlight. If you have just a light and it's sitting here in all directions, then that's good, but sometimes you need to focus the beam. You want to look at exactly this briefcase or look exactly at that wall outlet over there. So you focus the beam in the flashlight with a reflector. Well, here we use reflectors and directors, but one thing to remember is no energy is created. You also, if you gain in this direction, just like if you stand with a flashlight, it's dark behind the flashlight because you've directed that light in one direction. So similarly, no energy is created. What you do is you redirect the energy to be primarily in one direction. So that's how you create gain, but that's fine. That's good because if I want to talk to Australia, then if I can direct, I don't care that I can't talk to Europe then because I'm looking to talk to Australia. So I turn it around to where it's aimed toward Australia, and Europe's on the backside. If I want to talk to Europe, I turn it around to where it's aimed to Europe. So yeah.
When you're doing that, if you want to talk to Australia, is it best to shine it around the sort of equator direction, or can you go over Antarctica?
Yeah, you go over you use the Great Circle, what's called, and that's where, I'll see if I can bring a picture of one next time. But yeah, the way to tell you where you aim it is if you've got a globe, put your finger where you are and a piece of string, and your other finger where you want to talk to. And that will be the shortest route around the globe.
Direct shortest route.
That's right, the direct shortest, that's what you want.
Now, sometimes you want to work a long path, depending on the frequency behavior at the time. DXers will try to figure out whether they should work long path or short path to get to a certain place. And sometimes certain frequencies that will behave better for long path getting there are more advantageous to try for that particular time of the solar cycle or that particular time of day. And guys have written books about the theory on how to work DX, and some they can't work this country short path, but you can work a long path on different frequencies, the lower frequencies or whatever. So sometimes there's a strategy to work them the longer way, and the hardest point to ever work is exactly the other side of the Earth, where both paths are equal. Trans-equilateral are the hardest places, the hardest 2 points to ever talk to are trans-equilateral, because they're equally the other side of the Earth from you.
How does the fact that it's day on one side of the Earth and night on the other side of the Earth affect that?
It does, and that's why you have your frequency selection. And your ideal time, they used to make these little slide charts that were cardboard with a piece of plastic that slid over it. You'd see what time it was. It would show you where daylight is. Today, everybody just does it on the computer. But you want to find a time, like suppose 14 megacycles, 20 meters, you're going to get some what's called gray line propagation at dusk or dawn. So you want to find a time of day when it's dawn here and dusk there. So you're trying to spread this maximum, you're trying to align all that. And that goes into your strategy. If you're trying to work this one particular country, you're going to try to find a time of day when it's both daylight there, or it's both night there, or you get as close to overlap as you can. And then use the frequencies that will be behaving in the way you want them to behave at that time of day based on the sunspot cycle. And of course, when we have better access to the higher bands, there's more opportunity to use those because they're better during the high sunspot cycles. Today, when we really can't use anything above 14 megacycles, we're even more limited, which makes it harder to work DX. And if you really are trying to work one spot, the serious DXers, they calculate all this out and develop a strategy around that.
Sure, and sometimes long path does work, but typically it's short path.
Typically, it's short path. It's
By the
usually
way,
better.
we have a word of the day, antipode. It's the spot, you don't have to know this for the test, by the way. It's the spot on Earth that's directly opposite us. Your antipode is where, and like I say, it's the toughest place to work.
Okay, what is our antipode?
I don't know. I'll have to check.
Have you heard about the
Like
people
it's
that send
India.
a friend across the world and go to the antipode? And one person lays a piece of bread on the ground, another person lays a piece of bread on the ground, and made an earth sandwich.
Oh, really? That's good. Yeah, I like that. Good. Hopefully, the antipode is not ocean. So, because I wouldn't be bread would float probably.
Well, at least it'd be moist.
People have done the math about what parts of the earth actually have land on both sides.
Right.
It's
Oh,
actually,
sure.
it's actually a very small
Oh, yeah.
percentage of the
Yeah,
earth
because we're
actually
mainly
is
water, yeah.
not ocean.
But anyway, so yeah, but that's part of the thing when you're talking about long path. That's why having a rotatable array works very well. Again, and having something that you can focus your beam. If it's, again, typically you want to focus on the short path, but if you find out a long path is working, you turn it around and go the other way. Anyway, having a beam or directional antenna allows you to focus your signal in whatever direction gives you the best chance to talk to where you're trying to talk to. So that's why directional antennas are so highly desired, is that they do that. So again, we talked about with dB, gain is typically driven in dB, and it's with reference to something. You mentioned isotropic radiator is often used reference. It probably shouldn't be because it doesn't really exist, but you do see something. dBi is dB compared to an isotropic radiator. dBd is dB compared to a dipole. If it just says 8 dB, you don't know what the reference is. Probably it's a dipole, but you can't be sure. The American Radio Relay League and QST Magazine will not allow beams to advertise their amount of gain because people play games with those numbers. In fact, there used to be a magazine called World Radio, and they used to have a writer on antennas called Kurt N. Sturba, and he had worked for some antenna companies. He was an older guy. In fact, I think he ultimately passed away, and they actually brought in, Kurt N. Sturba was not his name. It was a fake name because there's such a thing called a Sturba curtain. So he was playing off of that type of antenna. But anyway, he was working at one radio place, or was maybe being told by an engineer that worked for the radio place, and they were coming up with a beam antenna, and they were talking about testing it and getting it to work and all this, and he said, when are we going to test the gain? And the guy says, we don't have to test the gain. We know how much gain it's going to have. And he said, really? He said, how much? He said, more than our competitor. So sometimes those numbers are not worth a lot that they tell you in the ads. And like I say, QST won't let them print the numbers. If they're going to tell those kind of tales, they got to tell them on their website. Of course, now everybody can go to the website. But anyway, they don't do that because gain numbers can be played with to make them sound better and make you buy one versus another. In reality, if you've got a 3-element beam, there's a few things you can do to optimize it, but most 3-element tri-band beams, and typically the 3-element beams are for 20, 15, and 10. 20 meters, 15, and 10 meters. Typically, there's not much difference between them. If they're all 3 elements and they're all tri-band, there's some compromises you have to make to have a tri-band antenna, but they're very similar. So, but each one of them wants to claim they have an advantage to everybody else. When you get into gain, remember we're dealing with 3 dimensions here. You're dealing with your azimuth. The azimuth is the fancy way of saying north, south, east, west. The plane that we're looking at. Elevation is the height above the horizon of what your gain is, and really you're getting gain in both directions. So you can have gain that is up high, you can have gain that is in a certain direction. This shows an azimuth pattern of a typical beam. Okay, let me mention one other thing. And it doesn't make much difference, well, it makes some difference at 20 meters. Typically, when we're talking about radiation patterns, forget about gain per se, but even any radiation pattern, that doesn't come into play until the antenna is at least a half wavelength high. Well, a half wave at 80 meters is about 130 feet. So unless you're looking at, there are not many, by the way, there are not many 80-meter antennas. They're extremely huge. There are people that have them, rich people in foreign countries that are DXers. I've seen a 3-element 80-meter beam, but literally you're talking about 130, 125 feet elements on the beam. So it's a huge mechanical monstrosity to get up and to keep up if you have any kind of ice or wind or whatever. But in any case, if you went to all that trouble, there's no point in doing it unless you can get it up about 125 feet. Because with the 80 meters, you're not going to be high enough that directionality is going to really come into play much. Same thing with even the directionality of a dipole. Most people's dipoles are not very directional, at least on 80 meters and probably 40 meters. 40 meters got to be up about 65 feet or so. So what happens is they tend to be more omnidirectional. But if you get them up a half wave, which on 20 meters then is about 35 feet or 40 feet, that's a little more reasonable. You can do that. And then the directionality starts coming into play. So that's why another reason, there's lots of reasons why you don't see many 80-meter beams, and you see only a fewer number of 40-meter beams. But that's part of it, is if you don't have them up halfway, then you might as well not worry about it. So this is kind of what it looks like. Again, actually elevation makes a difference. We'll talk about that a little bit later, but elevation, you think about, you want the beam to go in this direction very powerfully. What you may not realize is you don't want it at that angle, you want it at a lower angle. That's one of the things they talk about with different types of antennas, low angle radiation. And there's reasons for that. We'll get into that in a little while. Okay, what are the two components of a radio wave?
Electrical and magnetic.
Electrical and magnetic, that's right. What is the usual name for electromagnetic waves that travel through space? Radio waves, that's right. What type of wave carries radio signals between transmitting and receiving stations? We're playing the same game. It's electromagnetic. Again, you won't be lucky enough to get two of these questions to answer each other on the test, so don't bank on that. It would be nice, but it won't happen generally. What is the property of a radio wave that's used to describe its polarization? It's the orientation of the electrical field. The orientation of the electrical field is the property that's used to describe its polarization. What is true regarding the polarization of a vertical antenna or vertical antennas? What they're looking for here, what is true regarding the polarization of a vertical antenna if the electrical field is perpendicular to the earth? Okay, what can happen if antennas at opposite ends of the UHF or VHF line of sight radio link are not using the same polarization? What will be the problem? What will be the situation? Be weaker, that's right. The signal will be significantly weaker. Which of the following results from the fact that skip signals reflected from the ionosphere are elliptically polarized? What results? Well, what they're looking for and what results is essentially you can use either horizontal or vertical polarization with HF signals. What is meant by the gain of an antenna? It's the increase in signal strength in a specified direction compared to a reference antenna. Okay, feed lines. Again, another very important area of your station that in many cases are neglected. It connects the antenna to the transmitter of the receiver and the receiver. What you need, though, is it to be low loss. Losses occurs whenever it converts the RF to heat. And you don't put coax up to create heat, or you don't put feed line up to create heat. So you want something that's as low a loss as possible. Loss increases with frequency and with line length. So a given, let's say, coax cable will lose more at 2 meters, 144 megahertz, than it will at 80 meters, 3.75 megahertz. Because as it increases in frequency, the loss will increase. Also, it's proportional to line length. In other words, you lose more over 100 feet of line than you do over 10 feet of line. So it is pretty much directly proportional to that. You do not want it to radiate. There's actually a time or two that some people try to get on the radio, but in general, you don't want it to radiate. The antenna is supposed to do the radiation. The feed line is just getting the energy from the transmitter and receiver, or from the transmitter to the antenna, and then from the antenna back to the receiver. So that's why the feed line is very important. It's really important because of low loss. You really want low loss. Coax is the most commonly used antenna feed line. Not because it's necessarily the best, really more because it's the easiest to use. A coax cable is a center conductor surrounded by insulation, which is in turn surrounded by a shield. So here we got the center conductor, we've got insulation, we've got a copper mesh for a shield, and then we got the outside insulation here. The nice thing about it, it can be routed next to conductive surfaces, so you don't have to worry about you can just tie it straight to the power leg or leg of the mast that you're using, even if it's metal, and it won't cause a problem. So its ease of use makes it a popular feed line. Ease of use and really the fact that it's available in so many places. Okay, hardline is the best type coax cable. It's the lowest loss of them all. It's generally used at UHF and VHF because remember, the higher in frequency, the higher the loss. What literally you see, we used to have, actually I used to be a member of JARS, and we used to have a fellow that worked at the transmitter site near a place called Auburn. If you know where the tall towers are, that's what some people call Auburn, that area. And they had what's essentially a large piece of copper tubing with a small piece of copper tubing for the center conductor, and then spacers, which shows like this, spacers between them to maintain the distance, because you've got to maintain the distance between the center conductor and the outer conductor. And that was what they used for transmission lines at WRAL 1 and 1.5 and whatnot. It was plumbing. It was electrical, but it was actually the people that had to do that kind of stuff it was like plumbing work being done. We don't get into that because of the expense. Typically, this is what you see for us, hardline, which looks like coax, but this outer conductor is not very flexible, and this one's not either, but it's more noticeable here. If you try to bend it, you can have a problem. In some cases, you can bend it a little bit, but you have to be very careful. And then there's stuff that they call like semi-hard line or something that's supposed to be similar to hard line that you can bend a little more, etc. But that's used a lot at UHF, VHF, particularly for repeaters. But the reason more people don't use it at home is twofold. One, it's hard to deal with. Like we say, if you have to make any bends, it can be a problem. And two, it's expensive. Some people get lucky and find a cable TV company that's throwing some away because they use it and sometimes they discard it. But either that or you've got to be willing to pay a lot of money to use hardline in your home station. But you could well notice a difference if you do, because like we'll show in some subsequent pictures how the attenuation is, how much signal you lose for various types of coax. Open wire line, which is known also as ladder line or window line or parallel conductor feed line, that's a very common type of feed line, and it's great in many ways. The way it's not great, if you'll see, this has to be kept away from the tower leg, because it's, in this particular case, this is open, uninsulated wire, which tied together with spacers. You can build this yourself. You can build it yourself. This is what's called, those of you that may remember the old twin lead type wire that you use for old TV antennas, this is something similar to that, except they knock out little areas. They call it ladder line or window line, and it's like open wire, except it's fully insulated. But you still can't put that next to the tower leg, or if you do, there's problems that will occur.
It needs
So-
to be kept about 3 times its width
Right.
away from metal. So
Right.
if you've got, a 2-inch wide window line 6 inches away from anything. I will say I have one antenna that uses the open wire feeders like you see on the right, and another one that uses the commercially produced on the left. Technically on the charts, the higher quality is the open wire feeders. It is so much harder to work with that I will never use it again. I would use the commercially produced stuff, because what happens with the homemade stuff like that is it twists over and shorts out. It just flips. And you have to really make sure that that doesn't happen as you're going 150 foot up your pine tree.
Yet you have to turn it though every
Not
so-
you can't turn the homemade stuff. That has to be kept just like it shows in that picture, where it doesn't turn helically because it'll
Right.
short out. They'll fold over on each other.
Right.
So they have to be
Why don't you have sometimes you twist them to keep the wind
with
from.
the
ladder
plastic
line.
ones
Yeah, the
on
ladder
the
line,
left.
yeah.
You do. You put a helical twist in that, and
Yeah.
because of that center conductor plastic between them,
Right.
it maintains the space
Maintains
and
the-
keeps
yeah,
it
okay.
from shorting out.
Okay.
Whereas the one on the right, as you can see, if you flip that over, those wires would just
Sure,
cross
yeah.
over.
Remember, these are uninsulated.
Well, even if they're insulated, your impedance is gone. Because
Right.
the impedance is
Right.
maintained by the equal
The
spacing.
spacing, yeah.
And so with that kind on the right, you have to put a mast up every 10 or 15 feet
Right.
to hold it, which I do
Right.
across my backyard to the 150-foot pine tree.
Right.
That was a lot of work that I could have avoided with the commercial kind.
Right.
So antenna 2 uses that. Well worth the ease. The slight loss in quality is made up for by the ease of use, in my opinion.
And it's relatively small difference between the two. It's
Price
not-
wise?
No, I'm talking
Oh,
about.
yeah,
small.
well, very small.
Yeah,
very small, tiny.
Very small difference. So, as Carl was saying, again, you can build this yourself. I built some actually just for demonstration.
Yeah.
Actually, I was in Boy Scouts at the time, and we built some just to show how you do it. But I never actually used it. But I have used the ladder line quite a bit, and it's good stuff. And works.
It looks cool going across my backyard on those posts, and it's solid.
Oh yeah, I bet.
But the work, juice ain't worth the squeeze on that one, in my opinion.
Right, yeah, that's right. So anyway, these are both available. Actually, you can get a ladder line or a open wire line that you can get commercially.
Yep.
But it winds up being pretty expensive. It's the ones that I've seen of it is more expensive than the ladder line is. The ones that I've seen of it. But anyway,
Yeah, I bought an 80-meter dipole with 150 feet of that kind of feed line on it. And I think I paid about $150 for the
okay,
entire thing. And that was when copper prices were a little higher than they are now.
right, okay,
But it would have been a whole lot cheaper. That same antenna would be about $70
right.
with the commercially
Ladder
produced,
line, yeah.
easier to use.
Yeah. So anyway, so that's a good point. It's usable. Really, probably the best compromise, as Carl was saying, I was saying, is the ladder line. It works almost as well and is much easier to work with, but not quite as easy to work with as coax. The reason you have to keep it away from other pieces of metal is in the open wire transmission line and the ladder line, you've got currents flowing in opposite directions of each other. These fields oppose and cancel each other at the distance. They're very close together in terms of wavelength. Remember, on 80 meters, a half wavelength is 130 feet or 125 feet. So they're very close together in terms of wavelength. They're also a very low loss, and they're lightweight and relatively inexpensive. There's any number of places you can buy this stuff from. And in fact, that's another good reason to go to a ham fest. Usually, there's somebody selling some at a ham fest. You can see what it looks like versus some of the other types of antenna feed lines. Okay, feed line characteristic impedance. Remember, it's important for us to know the impedance of the feed line. That is, it defines a relationship between the feed line voltage and current. It is not a loss like resistance would be. It's just the match between the feed line and the antenna. Coax is typically 50 ohms. The cable companies use 75 ohm coax, but 99% of ham operators use 50 ohms. Open wire is usually either 300 ohms or 450 ohms impedance, and it has to do with the characteristic impedance of your antenna. Or at least its importance has to do with the characteristics. A typical half wave dipole is about 50 ohms. So you don't have to have any particular matching to it. It actually is a little over 50 ohms, and actually if you turn it to an inverted V, it becomes closer to 50 ohms. We'll talk about inverted V in a little while. All the energy, if it's matched perfectly, then all the energy sent down the line is accepted by the antenna and radiated. And that's as good as it gets. Essentially, you get the advantage of every milliwatt of signal you send down there gets radiated from the antenna. If it's mismatched, then some of the energy sent down the line is reflected back. And the reflected energy interacts with the forward energy to create what's called standing waves along the transmission line. So you've got something other than a 50 ohm antenna with a 50 ohm transmission line, and then some other it comes back. Now actually it gets reflected back. It actually gets reflected back until it dissipates, which actually creates heat in the feed line. But what you're doing is you're looking at the weight ratio of the two different, the high voltage and low voltage point. What happens is that when you have this standing waves created, you have points of high voltage along the feed line and points of low voltage along the feed line. And the standing wave ratio, SWR, is the ratio between the highest voltage point and the lowest voltage point. So if the highest voltage point was 30 watts and the lowest voltage point was 10 watts, I guess it should be 10 volts, 30 volts and 10 volts, the voltage along the line, then it would be 3-to-1 standing wave ratio. Now why is that important to us? Well, there are people that will first of all, before World War II, nobody knew what SWR was because nobody was using coax. So, and the radios using tubes in their final are not nearly as sensitive to standing wave ratio as newer radios are. So what happens is in those days, you cut the antenna as best you could. You used your open wire primarily for it. And your radio, which was a tube radio, once you tuned up the tank circuits and the loading circuits, then it would pretty much feed into the antenna, and nobody knew what SWR was, and nobody cared.
Even if you did, you made some minor adjustments to the antenna system until you got a dip in the RF.
Right, that's right, yeah. Yeah, you could, if you weren't measuring SWR, but you were measuring how well the transmitter would tune into the antenna.
You were coupling the RF energy.
Right, so you could make some trims to the antenna because of that. But anyway, now though, these solid state transmitters, it will mess up the final transistor, power transistor, if the SWR is above about 2-to-1. So what happens is they put in circuitry that starts cutting back the power to after it gets above 2-to-1. So if your SWR is better than 2-to-1, your 100-watt transmitter is now only putting out 70 watts. Or then if it gets above 3-to-1, it may only be putting out 10 watts. So it drops off pretty quickly, so you have a real strong incentive to keep the SWR below 2 to 1. Also, if you have a high SWR, you get increased feed line losses. So because all that essentially going back and forth causes the feed line to heat up and you lose more power. If you've got erratic SWR, that generally means an intermittent connection to the feed line or the antenna. So if it's bouncing all around, now one case that can cause that is, particularly with open wire or even lateral line, is rain. Rain can change the characteristic impedance of the lateral line in some cases, and it can cause, if you've got like a Balaam, we'll get into that later, and you're looking at SWR at your radio, it can cause the SWR to change. Generally speaking, it's not enough to worry about, but it's possible. So anyway, so what you want to have, if you don't have a perfect antenna or a good antenna, you want to have a tuner which will essentially tune the antenna and feed line combination to give you a 1.1 SWR, and then the transmitter sees 50 ohms of impedance. It's happy. It puts out its 100 watts, and then you've got you maximize the use of your antenna and power up your transmitter.
One way I've heard it said that I think loss in a feed line, help me understand it the best, is think of it as a toll road.
Right.
You have to pay $1 every time you go over the road.
Right.
And if you have a high SWR, your signal's going from your transmitter or your tuner to the antenna, reflect, going back and forth. And if it's a high loss, it's got to pay $1 every time it goes back. And so it dissipates very quickly in the loss. Whereas if you have low loss, maybe a low toll, maybe it's only paying a penny instead of $1 every time it goes back and forth, more of that signal will go out through your antenna, even though it's taken a couple paths up and down the feed line to do it, because it was a cheaper route over low loss feed line. And that helped me to kind of get my head around it a little better.
Right. Well, that's true. Essentially, yeah, the whole point is that when the signal's being reflected back, that's bad. You want all the signal going out the antenna. So however much is reflected back is wasted. It's not 100% wasted, but it's largely wasted.
Well,
So
it's going to reflect back out.
that's what I'm saying, but you lose each time you're making that happen.
Exactly. And if you have coax,
Right.
which has very high loss at a high SWR, you're really losing a lot. Whereas if you have ladder line, which has low loss, you're not losing that much.
Right, exactly.
And is it a property of just the line itself, or is it the line in the...
And the antenna, yeah, it's the combination of the line and the antenna.
So you could have potentially an inferior line that is matched to an appropriate antenna that is better than a mismatched higher quality line.
Yeah.
Yeah, technically, but you wouldn't normally have that. Yeah, that's right. Yeah,
In theory.
yeah.
Okay.
You want to view it as an entire system. Think of the whole thing, the feed lines, your impedance matching network, and your antenna itself as your antenna system. So everything the outside of your coax connector, your transmitter, from there on out is your antenna system.
Yeah, see, that's what I was saying here. This tuner tunes both the feed line and the antenna. Like you say, the system, the totality of it is, because that's what the transmitter is interested in seeing. It doesn't care about the pieces in between here. It just wants to see a good SWR there at its export. And let me mention one thing as a point of a lot of arguments. You might hear your first argument on the radio is about tuners. Some people will say the tuner fools the radio into thinking the antenna is right. The tuner doesn't fool anything, anybody. I'm trying to think. It's like if you have one of those little wall warts that runs your radio. It's taking, we talked about with transformers, it's taking 120 volts and converting it down to 12 volts or to 10 volts or 5 volts or whatever you need. It's not fooling your radio into thinking that's 5 volts. It's actually creating 5 volts. So similarly, the tuner doesn't fool anybody. It actually does match the antenna system to what the transmitter needs to see. Some people try to say it, again, almost like it's magic or it's something out of the ordinary. But in reality, it's just a tool that tunes the antenna feed line system to a match that the transmitter can accept. Okay, what happens to power lost in a feed line? Converted into heat, that's right. What is the common use of coax cable? Carries RF signals between the radio and the antenna. So that's what is the impedance of most commonly used coax cable typical in amateur radio installations? 50 ohms, that's right. Why is coax cable used more often than any other feed line for amateur radio antenna systems? It's easy to use, yeah. What generally happens as the frequency of the signal passing through coax cable is increased? If the frequency is increased, that's higher frequency, what happens usually? The loss increases, that's right. Which type of coax cable feed line has the lowest loss at VHF and UHF? Hard line, and here it says air insulated hard line. In general terms, what is standing wave ratio? It's a measure of how well a load is matched to the transmission line. Which reading on an SWR meter indicates a perfect impedance match between the antenna and feed line? 1-to-1. And by the way, I've been a ham for a long time. I've worked with a lot.
Yes.
What is the approximate SWR value above which the protection circuits and most solid state transmitters begin to reduce transmitter power?
2-to-1.
2-to-1, that's right. Continuing to talk about antennas, we're talking about building your own antenna. That's something almost everybody can do. You might not be able to build a transmitter or a receiver or whatever. In some cases, you can build some accessories, but almost everybody can build an antenna. And it's a lot of fun. It's interesting and it's rewarding. It's nice to be able to tell people this is the antenna that I built, etc. You can save some money. Wire antennas, and I have purchased some wire antennas, so I'm not faulting anybody who does this, but they're almost all overpriced. You can get the components yourself together and build the antenna for less than you can buy it for. And I'm not faulting them, they got to make some profit. I mean, I understand that, but I'm just saying you get the pride of ownership, the pride of building it yourself, and you can save a few bucks in the process. And again, since I started when I was very young, my Elmer, the guy who was helping me, and we built all my first antennas were all just wire and coax. In fact, sometimes we'll talk about, I think we covered that, pretty sure we covered that, a Balin, but I didn't even use those. You can get away without using them. And actually, I was in a discussion on one of the internet groups the other day, and they were saying, well, you have to have a Balin. You don't have to. May work a little better, but I didn't have one. I didn't have the money to buy one, so we did it without it. So there's even some ways you can cut corners to save a little money if you have to. Most of what we're talking about, I was just talking to somebody during the break, most of what we're talking about is about building HF antennas. You can build a 2-meter antenna, and there's several ways to do that. In fact, I'll tell you, when I was at NC State, where I went to college, I had 2-meter radio in the car, and I had a 2-meter 5/8 wave antenna, which we'll talk about in a few minutes, on the trunk lid. They got stolen, mainly because they looked like a CB antenna. And this was in the mid-70s when the CB craze was at its peak. So it got stolen again, and I found out that you could take I actually got stolen a couple times. The insurance company was beginning to question whether they were really being stolen. I was just trying to turn in and get some money, but I was not. But anyway, I found out these were 5/8 wave, that I could get a 19¼ inch piece of coat hanger, metal coat hanger, put it into a RG, SO239, yeah, I'm trying to think of the name. And make a little antenna that would work. And I did, and it worked. And later, little 19 and a quarter inch coat hanger spike. Later, my car got broken into, and they stole my ham radio, and they even stole the little coat hanger antenna. They were that desperate. I guess they figured it goes with the radio. So I had literally, you could tell that it was coat hanger. You had like a little kink in the wire where I had unbent it, but they still stole it. So anyway, that's just, but you can build your own antenna, but people don't tend to do it as much at 2 meters and 440 as they do maybe on the HF bands. Your antennas we talked about earlier is most critical of all your station components. If you spend money and time on your antenna, it'll give you your best return on investment. And if you know a few fundamentals, it'll allow you to design and erect your antenna, but also it'll allow you to appreciate what the commercial antennas you're looking at buying are doing. It's just like being able to know how your car engine works. If you have some sense of how the engine works, you're better able to, even if you have to pay somebody to work on it, to know what they've done, if they're doing a good job for you, etc. So it's always useful to know some details about how these things work. And then if you want to build one, you can do that, or if you just want to make sure the one you purchase is the best for your needs, then that's important too. A lot of people like to run low power. This particular cartoon, the guy says, yeah, I am just running 5 watts QRP, but I guess I do have an above average antenna system. So he's got a tower bigger, looks like the leg of it's bigger than his house. Anyway, so yeah, if you can have a little power and the greatest antenna in the world, you'd have a pretty powerful signal. So, by the way, somebody mentioned Voice of America. They used to do tours. I don't think they're doing tours anymore. Somebody said they stopped after 911.
You have to make a special request.
Oh, do you?
Yeah.
Okay.
But they
Well,
will.
anyway, we toured it I've toured it actually 3 times. But the funniest thing or the most interesting thing to see is something you don't have to tour it to see, just drive it on the road. And that is when you go to Voice of America, over a semicircle, if they haven't taken them all down, I think they still got them because there's no reason to take them down yet. But they've actually shut down one of the sites, but one of the sites still working. Over a semicircle, about 3/4 of a mile in diameter, or in radius actually, you're seeing sets of 4 towers, 4 200-foot towers, holding these broad, what they call curtain arrays of antennas. And the reason they did that, they couldn't rotate these antennas, so they had essentially where they could have a semicircle that if they wanted to go in this direction, they fired up this antenna. They wanted to go in this direction, they fired up this antenna. And they had literally about 8 or 10 antennas, each of which had about 4 200-foot towers holding them up. So that was, you're talking about your best antenna you could possibly get. I've heard stories of people at one of the VOA sites in Ohio, I think it was, that has been dismantled. But before they dismantled it, some hams got on there and used their antennas to work for a little while. And they made some tremendous contacts because these are just monster antennas that.
The Brightleaf Radio Club in Greenville has access to the decommissioned site, and they have a club station
Oh, do they?
that hooks
Okay.
into the VOA antennas. And I go over there and work for the North Carolina QSO party. And the funny thing about it was it's not very good to work the North Carolina QSO party from, because the goal of the North Carolina QSO party is to work every county in North Carolina. And we were beaming Europe. And we kept working Europe, and we finally had to go out and throw up an off-center fed dipole about 10 feet off the ground so that we could start working North Carolina contacts. But they do have access, and if you call that club, look up their website, they'll take you out there and let you operate from it.
Okay.
It's a club station.
Well, I knew there had been the people in Ohio, before that one got torn down, they did it, but I don't think I knew that they were.
They're not allowed to modify the antennas. They have to leave them as is. So as they
Right.
deteriorate over time, they will fail. But as of today,
Right.
they've got a log periodic dipole array, and they've got use of 2 rhombics.
Right, okay.
Beaming Europe.
Yeah, well, that's
Yeah.
great. You probably do good with 5 watts on that, wouldn't you? Unless you got a feed line loss enough that there's
They use
power.
a ladder line, 450 ohm
Yeah.
twin lead.
Okay, well, here's a halfway dipole. We've been talking about it, and this is kind of the nuts and bolts of it. essentially you have a half wave antenna, you've got two quarter wave halves split in the middle. Dipole actually doesn't mean absolute middle, but it means two pieces. And so it's generally parallel to the ground, so that means it's horizontally polarized. And that's really about all you need. You've got a wire here, quarter wave wire here, quarter wave wire here, some insulators, then feed line, which may or may not be coax, and that's an antenna. And that's really the antenna that most antennas should be compared to, because that's what most people can do. The big number and the number that I remember all the time is 468, because it's 468 divided by frequency in megahertz. And that gives you the length of a half-wave dipole in feet. So it's just, and 468 are easy to remember. These are some calculated dipole lengths done for you. So you see at 80 meters, 3.725, that's 125.6 feet, etc. Now, I just told you 19.25 inches. If you look at 2 meters, it says 38. Remember, that's a halfway dipole. What I was looking at was a quarter wave width. And that's at 147 megahertz, and I think I was down at 146, or anyway. But it does work even for 2 meters. You just have to convert the feet to inches. You see bolded there, 6 meters, 50.1 megahertz, 112 inches. That's bolded because it might be a question at some point. So you may want to pay a special attention. You can sit down and calculate it, and it's, like I say, it's very easy to calculate, or you can just remember 112 inches, whichever is easiest for you. Okay, as we were talking about, when you've got a low SWR, in this particular case, so this is not perfect. This is showing, this is SWR 1, 1.1, 1.5. It's barely dipping below 1.5, but it only has that one resonant frequency at one frequency. As it gets further away, SWR is going to get higher. And 80 meters is particularly tough because as a percentage of wavelength, 80 meters is kind of a big band. So 500 kilohertz is a long ways when you're in the 3.5 to 4.0 range. So typically you have to cut it for part of 80 meters, and then you just either have two, one for the code area and one for the voice area, or you use a tuner or something like that. So your best SWR is going to be at one frequency. As you move away from that one frequency, it's going to be get a little worse and a little worse. In this case, where we talk about 2 to 1 SWR, we see you got a bandwidth here of about 3.65 maybe to about 3.85 or something. So in this particular case, if you wanted to keep it, oh no, I was going there. That's even shorter. That's 2 to 1 is what we need. So anyway, so you would only get a certain amount of bandwidth there, and even then you would have an SWR that was higher than your transmitter could really handle. So that's why you have to in some cases, which 80 meters, have 2 antennas up or use an antenna tuner. Okay, in practical antennas, you've got the dipole. The strongest signal is off of the broadside to it. The weakest signal is off of the ends. But remember, that's generally for a dipole at 1/2 wavelength high. If it's less than that, then you've got less directionality. Now, there is something else called an inverted V. If really you're going to have a V almost however you do it, except for the people with the most expensive installations. If you have 2 trees, let me draw the trees here, and a tree, and a tree, and you support it at either end, it's going to sag on you.
the weight of the, first of all, weight of the feed line, and also you've got, you're going to have a bit of a sag there, because that's gravity. What some people do, if they have one really good tall site, say they've got one tree that's better than all the rest, is they'll put the center of the dipole at the tree, and then the legs will slope down, and you might even tie it off to a fence here. You've got a fence. What you would need to do is make sure you have an insulator there. Essentially, you don't want anybody to be able to touch the wire because they could get RF burns from it. But if you had it far enough away that this rope would wind up being up to maybe 8 feet or 9 feet from there to there, then it would be pretty safe to do that. And this is what's called an inverted V. An inverted V actually is closer to omnidirectional than the standard dipole is as well. Plus, again, most people use inverted V's for 80 or 40, and like I say, in those situations, you're not going to get all that much directionality anyway. Yes.
In the situation where you had two trees, does the location of the feed line make a difference? I mean, if you just ran the feed line off of one end and down.
That's an in-fed antenna. That's a different animal. It's more difficult to make it work well. You can do
The feed line
that.
should be in the middle of the dipole.
Yeah, for a well, it wouldn't be a dipole then. At what point, if it goes to the in-fed, it's considered an in-fed antenna. It can be a half-wave in-fed antenna, but its characteristics are much different, and it's harder to get it to work properly because you've got, I was trying to think if we showed this last week, you've got essentially we were talking, this is something we're talking about on the internet. You've got essentially voltage, you've got voltage distribution like this, something like that, essentially, going all along the antenna. And that works out because it's balanced. If it becomes unbalanced, there's all kinds, now there's definite types of unbalanced antennas, but you get yourself into a whole host of problems that you don't have if it's a balanced antenna. So people do use in-fed antennas, and you can do it, but you have a series of problems that you don't have with a dipole. That's why most people that can run a dipole use a dipole.
Just because I'm thinking in my own particular situation. If you had 3 trees,
Right.
can you run the feed line down the middle?
Oh, sure. You can do that. And like we say, I mean, on an 80-meter dipole, this is going to be, 60, 65 feet apiece. But as long as you've got more than 65 feet, your rope can handle the rest of it. So if you've got 80 feet here, then you've got, say, 65 feet on this leg and then 20 feet of rope or 15 feet of rope. So, and the same thing on the other side. And it doesn't matter if it sags. I was kind of making a joke about it being a V, whichever way you do it. But if you can get supports on both sides, it doesn't matter if it's going to sag a little bit. It'll still work. It'll work fine.
In real life, every antenna I've ever seen has had unequal height. No two trees are exactly the same height. The
Right.
branch in the front yard is a little higher than the back of the branch.
Sure.
In real life, there's a lot of wiggle room, and it still works just fine.
That is one of the reasons, though, why antennas can seem to be an art rather than a science. And that is, you can model on the computer all you want to, but you can't model even the conductivity of the trees that you're hanging them from, and how many power lines are close by or not so close by. And so that's why people will say, ultimately with an antenna, you've just got to put it up to try, because you can't totally model or predict exactly how well it will work. It may work great, or it may not work so well, but really at some point, just put some wire up and give it a shot. Wire's not that expensive, and and you can do it. So this show, yes, go ahead.
Is it best to just put it as high as possible?
Typically, yes, you want it, I mean, again, if you talk about 300 feet, that not necessarily, but for most of us, something 60 feet and under, you'd rather get it closer to 60 feet than lower. I mean, if you're, like I say, if you're next to the WREL TV tower that's 2,000 feet, I wouldn't necessarily put it at the top of that, but for what 99.999% of us have, yeah, you want to get as high as you can.
What's like the regular height? I mean, is it 10 feet off the ground? Is it 60 feet?
No, it's really whatever trees you got. I mean, it's like you were talking about, you said you did the one at the VOA and it was about 10 feet off the ground or
Yeah, well,
15 feet.
I'm sure you talked about the different types of propagation that you do for close and stuff, and we'll talk about it next week. But sometimes if you're looking to talk close in, like I'm net control tonight of a net that covers all of North Carolina. And we really don't care to talk to anybody outside of North Carolina. We're a traffic net for North Carolina, but I want to be able to talk to everybody in North Carolina on 75 meters. So an antenna system that works well for that is to have an antenna that's relatively low to the ground to wavelength. The way that it behaves, the RF tends to make a big bubble around, so you don't get that far away, but you get very good coverage close in. For that goal, and that's what we ended up doing at the QSO party, we wanted to just talk locally. I would say generally we want to get our antennas as high as we possibly can. For most of us, that is somewhere between 30 and 60 feet. Most ham radio operators probably have their HF antenna somewhere between 25 and 60 feet. We are fortunate here in North Carolina, we have a lot of trees and we have a lot of tall trees. So I have an antenna that's at 100 feet because I have a loblolly in the backyard that's just great antenna tree. You go out to Kansas, they don't have those luxuries. So they're going to have a 20-foot mast that they're able to put up in their backyard. So, take the average of that. But, as high as you can is a general rule. And you probably won't ever go too high because your trees are only going to be so high. You're only going to be able to put up so much tower or so much mast.
Right. For instance, people that I know one guy that's a heavy DXer, he works for many foreign countries. He's got a 110-foot tower. He's the only person I know that has one like that. And even for him, I mean, there's a limit. You wouldn't go more than 110. In fact, most people, even if they've got a nice tower, is not more than 70 or 80 feet.
Well, you think about what wavelength you have. Think of your antenna height in terms of wavelength of your desired frequency. And when you get above one wavelength, there is a diminishing return. Really, when you get above half a wavelength, there's not that much improvement to go from half a wavelength above ground to one wavelength. And there's precious little to be gained to go above that. So if you're looking at using 14 megacycles as your DX frequency, going much higher than 20 meters above ground is not that beneficial, and the costs are significant, the maintenance is an issue, and you have feed line loss. Because you have to remember, every foot of feed line that you put up there is more loss for your signal. So there becomes a diminishing return.
That especially becomes important, actually, with 2 meters and 440 megahertz. A lot of times people, I've known people, and scanner listeners as well, that'll put up about a 30-foot tower, and they'll listen and they say, I can't hear as good as I could hear with the little antenna that was just on the roof. Well, it's because they use cheap coax. And literally, the loss in the coax is greater than the gain they got by putting the antenna up at, say, 20 or 30 feet, as opposed to having it just on the top of the house. So, but again, that's another expense. So when you're looking at going up high, you've got to look at all the expenses. And even on HF, when you start getting at those kind of extreme, well, that's one of the reasons I'm sure you use lateral line or open wire.
Work with coax. That's
Yeah,
exactly right.
yeah,
I've got
you do.
150 feet of feed line to the antenna.
Yeah, so
I
that
had
would
to
be.
do that with coax.
Yeah,
I had to
you-
use hard line, that costs
Oh yeah, a bundle.
a
Yeah.
bundle, whereas
Yeah.
the open wire feed line's cheap and,
Right.
yeah.
So you're always balancing various aspects of the antenna. But again, for most of us in most situations, the higher the better. But there can be extenuating circumstances. If you've got, of course, if you've got an unlimited budget, then you can use hardline all the way up
Sure.
120 feet or whatever.
Yeah, right.
Anyway, if you ever get a chance, if you look through some of the magazines, look at the people in Europe. Lots of the hams in Europe, or a certain number of hams in Europe, tend to be very, very wealthy. And so they do, and they don't even, they live in an apartment downtown in Copenhagen or somewhere, but they own a farm out 100 kilometers away, and on that farm, they just go crazy.
A lot of
they'll
that's
put up-
clubs too. A lot
Yeah,
of
that's
them
it. Some
come
of them
together,
clubs,
like
yeah.
4 or 5 guys will
Yeah.
form a club and they'll go buy the land outside.
Oh,
You
yeah.
know.
So you'll see some wild stuff. And in their case, it's not necessarily as high as you can get it. We're balancing all kinds of things at that point if you got that kind of money. But most of us don't have to worry about that. So, but anyway, this is what a halfway dipole pattern looks like over at a halfway over ground. This is what it looks like in free space, but there's no, and sometimes you'll see what's called the figure 8 pattern here. And that's what they'll show as kind of the azimuth gain pattern. But in reality, you almost never get that because you're not in free space. You've got ground 30 feet away or 60 feet away or even 100 feet away, and it changes that pattern. Another practical antenna, a quarter wave, essentially can be thought of as a dipole, halfway dipole, where you've got 1/4 here, and essentially the radials wind up being the other half of the antenna. So a quarter wave antenna is really, again, based kind of on the halfway dipole, but it uses radial wires for the other half. If you're dealing with HF, radials minimize ground losses, so you need a bunch of ground there. A lot of people will tell you, or you'll read, that you can just put this vertical up and drive in a ground rod and connect to it, and you don't need any vertical, or you don't need any radials. Can you make contacts with that? Yes. Is it really good? Are you making the best use of your antenna? No. If you can put radials out, they'll make a huge difference. And just recent research has shown, in this particular case, when we were showing just a minute ago, this kind of assumes that these are all quarter wavelength, because you're saying we're taking this half of the antenna and putting it out as radials. But it has been shown now that if you can get 2 or 3/4 wavelength, if you can get a bunch of even shorter ones, that helps a lot. Just some research that was published in QSD in the past year or so has shown that you'd like to have 2 or 3 full-length radials, but if you can't get a bunch of full-length radials, if you can even get a lot of short radials, that makes a tremendous difference in how efficiently the quarter wave works. So,
Are those radials on the ground?
well, it says right here, let's see it. Yeah, you can bury them up to about an inch or so. If you go deeper than that, you wind up getting into ground losses. But ideally, you could put them on the ground. That'd be great. The problem most people have is mowing the grass and stuff like that. So they try to get them an inch or 2 below the ground, and so that it doesn't mess up the grass mowing and whatever. And something else, as we'll see here, if you are high above the ground by wavelength, remember by wavelength, as a 2-meter antenna would be very high above the ground, 3 or 4 radials are about all you need. That's again but HF verticals are typically on the ground or right at the ground. But if you can get several wavelengths above the ground, then you don't need so many radials, just 3 or 4 will do well. Okay, here's the formula for quarter wavelength antennas. I don't use this because I just remember 468 and cut it in half. 468 is halfway dipole, and if I want a quarter wave, then I just cut that in half. Anyway, it's 234 divided by frequency in megahertz gives you length in feet. And if you want to remember how to do it in inches, I just get the length in feet and multiply by 12 to get inches. But whatever formula works best for you. Again, I have in bold 2 meters at 146 megahertz 19.2 inches, and that's in bold because you might see that on a question on the test. Again, you can calculate it. Like I said, those of us that have worked with 2 meters for a long time just know it's about 19.25 inches. That's something I have memorized without even trying to memorize it. Vertical antennas are primarily omnidirectional. They broadcast equally in all directions. Most repeater and mobile antennas are almost universally vertical. One thing that a 5/8 wave will do that a quarter wave won't do is you get a little gain in the horizontal direction. Essentially, a quarter wave, you've got like a bubble over the car. With 5/8 wave, it winds up flattening out into more like a donut rather than a bubble over the car. And that generally gives you a little more range out to repeaters that are further away. Also, if you're operating HF, quarter wave antennas are too long for mobile operation. Again, that would be for 80 meters, a 65-foot antenna sticking off the whip off the back of your car, which the policemen, and you'd have trouble going under overpasses and all kinds of stuff. So they do physically shorten the antenna by using some inductive loading, and you don't get something for nothing. That antenna is less efficient than a full-size antenna. But if you are on a car, you can't have a full-size antenna, so you use what you can use. Okay, here's this shows a quarter wave vertical and a 5/8 wave, and you can see the quarter wave has higher takeoff angles from the antenna. The 5/8 wave tends to flatten it out and give you a little more in this direction, which is where you really need it typically. This has a primary angle of radiation at 25 degrees, and this one has it at 15 degrees. So it gives you about 2.5 dBs above a quarter wave antenna. There are some people that don't like 5/8 waves. There's different arguments they'll give you, but most people that can choose one or two will choose a 5/8 wave rather than a quarter wave if they don't have to go under a parking deck or something that causes them problems with it. Rubber duck antennas are lousy. That's about the main thing you can say about them. But why do we use them? Because they're very convenient. Actually, for those of you that saw the video last week, remember Jeff and KN4NQ, Gary talking about why do you use one? Well, it's very convenient. They're small, they're mechanically robust, they're relatively inexpensive, but they're poor performers. I didn't bring in my radio this week, but if you saw last week, remember seeing, I had about a quarter wave antenna. I did not have the stock antenna that came with it. About a quarter wave antenna will do substantially better for the same power. And so almost every handheld radio I get, I buy additional quarter wave antenna because it's only about 19 inches, and I can, even with on my hip, 19 inches only goes a little ways up my back. So I'd rather have the inconvenience of a quarter wave and get the advantages from a performance than to have a little bit shorter rubber duck. But lots and lots of people use them with repeaters. They work pretty well because you don't have to have the great antenna. Now, if you're going to be inside a car, you do not want to use your rubber duck inside a car. What is a car? It's a metal box with a couple of windows and whatnot. I used to travel quite a bit, and I had a little mag mount antenna that I would put on top of the rental cars, and I tied into my handheld, and I had a really good job. In fact, that's what I had when I was talking about being in Calgary, Alberta, Canada. Was a handheld with mag mount on the car, rental car. So that makes a tremendous difference if you want to talk to somebody from inside your car. Get, at the very least, a mag mount antenna. Get your antenna outside the metal box, and you'll do much, much, much better. Okay. How do you describe a simple dipole mounted so the conductor is parallel to the Earth's surface? What is that? If it's parallel to the Earth's surface, what is it? Horizontally polarized. So what you have there is a horizontally polarized antenna.
What is the disadvantage of rubber duck antenna supplied with most handheld radio transceivers? Yeah, they're not real good. It does not transmit or receive as effectively as a full-size antenna. That's just, now with what you already know about antennas, that should be self-evident to you. How would you change a dipole antenna to make it resonant on a higher frequency? We didn't cover that, but remember wavelength. If we are at a higher frequency, what does that mean about wavelength? It gets shorter. So if we had to make it resonant on a higher frequency, we would make the antenna shorter. So that's what we would, you just shorten the antenna and make it resonant. Why is a good reason not to use a rubber duck antenna inside your car?
It'll suck you more.
This one, yeah, signals can be significantly weaker than when it's outside the vehicle. That's the official. Okay, what is the approximate wavelength in inches of a quarter wave vertical antenna for 146 megahertz? 19.2 or 19 and a quarter. But anyway, yeah, that's about it. What is the approximate length in inches of a 6 meter half wave dipole antenna? We mentioned that one specifically. 112 inches, that's right. Now remember, you can calculate it out. You don't have to remember 468 divided by frequency in megahertz will crunch it right out for you. So if you happen to forget it, just remember that 468 divided by frequency in megahertz.
Is that 112 inches? Is that the same as those big long antennas that used to be on police cars?
No, they were actually for like, some of them were 49 megahertz, and some of them were even for lower than that. They actually, that's a CB antenna was like 108 inches, and they're some of the ones that you see pulled over too. So they were for different frequencies. Now 112 inches is, but that's also, remember, that's a half-wave dipole. On a car, you're typically seeing a quarter wave. So that would be 60 inches or 55 inches or something like that, 56 inches.
In the old
So-
days, it was in the 50s, and so when it mobile operation, it was standard to put an 8-foot width on the car, and you just coupled into that.
Right.
As best you could, that was your tube transmitter.
Right.
And the military mobile radios used to just couple into 8-foot whips. So you did see some guys who just spring mount an 8-foot whip, which is about right for 10 meters or CB.
Right.
Yeah, highway patrol used to be on 6 meters.
Something like that, yeah.
Close to that, yeah.
But they use the long whips too, for a long time. Okay, what is the reason to use a properly mounted 5/8 wave antenna for UHF, VHF mobile service?
It has a longer range.
Yeah, there's two aspects to it. It has a lower angle of radiation, if you remember the picture we saw, and more gain than a quarter wave, and so it usually provides improved coverage. That's the official answer for that. Why are UHF and VHF mobile antennas often mounted in the center of a vehicle roof? Well, we didn't actually cover that. It showed we got a picture of it, but the ground plane underneath it, the radials, the metal acting like radials underneath it, is more equal if it's in the center of the car. So it says, in this particular case, the official answer is a roof-mounted antenna normally provides the most uniform radiation pattern.
Yeah, the car itself acts as a radio.
That's right. The car itself is the radial, as we were talking about. So you're half the antenna is the vertical part that's all mounted to the car, and the other half is the body of the car. And if it's in the center, then you've got more uniform metal around it in all directions, and so that makes it more uniform. What is a common type of loading when referring to an antenna? We touched this briefly. You insert an inductor into the radiating portion of the antenna to make it electrically longer. So you put an inductor in there. And again, the inductor will get warm. You don't want it to get warm, but it does. Again, your antenna is just not as efficient. So that's why you wouldn't use one at home if you can help it. But in a car, you can't have a 60-foot antenna off the back. So you have to use inductors to make them work. Any questions on that? Okay. Beam or directional antennas. We talked about them briefly. We're going to do a little bit more. They focus energy in a single direction
and they receive best from a single direction. And that's an important thing to remember. If you double your power, then that's great, but that only helps when you transmit. If you double your power through an antenna, if you get an antenna with 3 dB gain, it also has a 3 dB gain in receiving, so you can hear better where the antenna is pointed. So that's another reason why antenna can be a better investment than an amplifier. Antenna can be your best investment because whatever gain you get both ways. You get transmitting and receiving. If you get an amplifier, you just get it transmitting. 3-element Yagi, we talked about this briefly. This is another picture of one. Actually, I have a Mosley TA33 Junior. It looks kind of like this. It has a directed element, 1 or 0 or more. You've got a reflector, driven element, and director. You've always got a driven element. You have to have one of those. You usually have to have one reflector element. If you just have a 2-element beam, which they do exist, you typically have just a reflector and a driven element. If you put the 3rd element on, it's a director, and then if you add more, it's just additional directors to make it even longer and have greater gain. Another thing we talked about, it allows you to hear better in this direction it's pointed. It also allows you, if you've got stations interfering with you from behind or the sides, there's usually what's called front to back ratio. That's the difference between the strength of the signals in front of it and behind it. So if you're having a station that's really causing you problems interfering, you can turn it around to where they're nulled out, or nulled at least as best you can. And so that is another advantage you get. So having a beam is a very nice thing to have. It certainly works out well and gives you lots of advantages if you can have one and can get one at your location. And it's the most common directional antenna. Like we said, there's tons of places you can buy them from. You can do plans to build them, etc. So it's extremely common. A cubical quad antenna is a great antenna. It's one wavelength wire loop. In this particular case, a 2-element has a parasitic reflector loop, and it may have one or more director loops. It can be horizontally or vertically polarized, depending on exactly where you feed it. Whether you feed it along the bottom or you feed it along the side. They're great antennas. I knew a guy that had a 4-element cubical quad when I was a kid, actually before I ever got licensed. And it was a magnificent thing to see. Unfortunately, we had an ice storm, and his antenna just totally collapsed. It was a beautiful antenna, but the ice, it just couldn't handle all the ice on the elements and whatnot. So he never put it back up. I guess that he had all he could take. But anyway, they work great. Generally speaking, and this is in some of the antenna books, a 2-element quad is considered to have about the same gain as a 3-element beam. But you still don't see that many quads because they're 3-dimensional, they're just a little hard to keep up. Again, they tend to be more susceptible to ice damage, etc. But for people that have them, they generally love them and they do a great job as long as you can keep them in the air. Above 1 gigahertz, dish antennas provide tremendous gain in a reasonable size. Of course, we've all seen dish antenna direct to TV dishes and dish TV dishes, and so that's why they're using them, because they provide great gain in the above 1 gigahertz range. Okay, typically vertically polarized signal has higher ground losses than horizontal ones. So for long distance communication on UHF and VHF, they almost universally use horizontally polarized antennas. Now for repeaters and FM in your car, that's almost all vertical antenna. But if you're dealing with weak signal work, that kind of thing in UHF and VHF, they're almost always horizontal. In fact, that's how you can tell if the guy's using them for for VHF, UHF, single sideband, or if they're using it for FM repeaters, if it's horizontally horizontally polarized, then it's usually long distance, single sideband. If it's vertically polarized, he's generally hitting repeaters with it. Now again, you can have reflections, and you can actually use reflections in some situations. If you don't have a direct line of sight, so there's some big obstruction here, you might actually be able to bounce a signal off of a building or something like that. I was involved one time with a transmitter hunt, which is where somebody hides a transmitter, and then people try to find it. It's like they call it a fox hunt sometimes, but it's a transmitter hunt. And these people took a antenna and they put a beam in the park, mixed it up above the trees, but they pointed the beam into downtown Raleigh. Well, it hit all these buildings and it scattered 50 different ways. So it made it really, really difficult to find the transmitter. Well, I was not the person that found it first. Somebody else found it. But it was an interesting little trick they pulled. So you can use reflecting off buildings can help you, and sometimes it can hurt you. So it depends on the situation. RF connectors, we talked about that. Yes, Appeal 259 was the one that I inserted the coat hanger into to make a quarter wave antenna. That's like one of these. They're commonly used, they actually are called UHF connectors, but they're almost never used at UHF. Remember, a lot of these things got their names right after World War II. And after World War II, I guess this was hot stuff at UHF, but it's no longer the preferred connector for UHF operation, but it's still used, and it's used primarily now for HF frequencies. This is what they look like. This is how they look like installed on the coax. This is an adapter actually to use on RG58, the narrow or the smaller diameter. And if you want to see how to install them on coax, there are some excellent videos on YouTube. And I can tell you almost without exception, it's not as easy as they make it look on YouTube. Those people on YouTube are really good, and they do really, I generally put on maybe average of 2 a year. And I'm not really great at it. I'm decent at it, but I'm not great. In fact, more recently I got a crimper, and I wound up crimping them rather than soldering them in some cases. I've been experimenting with both of them. But you can put them on yourself, and if you do more of them, the better you'll get at it. The situation is most of us don't need to put that many on, 2 or 3 a year maximum, and so we never get that good at it. But you can put them on yourself and solder them. It takes a good soldering iron. You've got to have a good hefty soldering iron to do it because you've got to get those things pretty warm, but it is doable. This is what the SO239 jack, the PL259 is the plug, if you want to call it that. Then the SO239 is the jack, that's the UHF connector family, typically used up through about 2 meters. Once in a while you'll see something in 440 for it. The barrel connector is a great device because if you've got a long run of coax like we do sometimes at field day, you essentially put one end of your coax in there, the other end in there, and you've now got 200 feet of coax. The downside is you don't get something through nothing. You usually get about a 1 dB loss through that connector. So you lose something. But if you need it, you need it. But that's what's called a barrel connector, as you can see, PL258. Okay, the end connector is really probably the best connector around. That's this. It actually works better. It's used mostly at UHF and above. It's moisture resistant, which is the PL259. It's not. It is useful to 10 gigahertz. It's very, very solid mechanically. These are very hard to put on coax, and they're expensive, which is why you don't see them used a lot. But when they're used, when they're professionally put on and they're installed and they're done right, it makes a great connector. Again, the moisture resistant is worth a lot. A BNC connector is what used to be used on most of the handhelds. And so the older handhelds you see, that's what you'll see on them is a VNC connector. And that's still reasonably common, but the new smaller radios use what's called an SMA connector. And that's a picture of those. So the only thing about these you have to remember, and I have to remember it when I'm getting my 19-inch whip on the handheld, these are not terribly mechanically rigorous. So I have, my 19-inch antenna is very flexible, because if something's got to flex, the antenna needs to flex, that does not need to flex, because it won't flex much, and it'll break, and then we're back to spending a lot of money to get the radio repaired or trying to get in there with a magnifying glass and do it myself. Okay, these are adapters. You can get adapters to almost any two types of coax. There is a little company who, name I forget, I used to be on their mailing list. They make connectors for everything, literally everything. Pardon?
Amphenol?
No, that's a brand name. This was actually a company that sold different brands. But anyway, the downside is that their cheapest adapter was like $10. They were expensive. They had whatever you wanted, but they were not cheap. But if you're willing to spend the money and search for it, you can get an adapter that will adapt just about anything to just about anything else. And literally, whenever I was up in Calgary and I was talking about using these antennas on the car, this is what I used. Because my handheld in those days used a VNC connector, but my magnetic antenna used the PL259, so this actually made the adapter, and so I could have my handheld transceiver, and then feed it into an outside antenna. Like I say, it worked pretty well. Okay, moisture is the mortal enemy of coax. Water contamination is one of the most common failure modes of it. One of the other thing is ultraviolet light can degrade the jacket. So if you can, you want to choose a UV resistant type of jacket for it. Air core coaxes require special care to prevent moisture ingress. Actually, at places like WRAL, they use nitrogen overpressure. They literally pressurize it with nitrogen to keep out the moisture. So that's what the big boys do, but they got money. So you have to have other ways of sealing it. But even sealing it sometimes doesn't work, because if you seal it and it has a certain amount of moisture in the air, it will condense on the inside after it's sealed. So not even sealing it well is always the answer. So moisture is something you've got to really work at to try to overcome. This is the chart I was telling you about. It's pretty hard to see. You can get this chart is in most antenna books. It is not in your book, and you don't have to have it for this. But essentially, this shows you this is the attenuation in dB. This is how much you're losing. This is the frequency. So just here at 150, which is right around, you just see how much more you're losing with a typical. Most people don't use open wire. This is 7/8 inch hard line, which is extremely expensive. This is, by the way, usually attenuation per 100 feet. So if you have to have 100 feet of even hard line, you're going to lose 6.6 dB. That's the best stuff you can buy, more or less. So at 150 megahertz, that's why if you can keep the cable runs short, you're going to help yourself, because you just lose a lot going through coax at that frequency. Now, if you look down here at 4 megahertz, which is 80 meters, then you're only losing 0.6 megahertz with RG52. I see RG58 is about 0.7. So it's much easier to use coax, or if you pay much less of a penalty of loss with coax if you use or you're at lower frequencies than if you're at higher frequencies. By the way, I do not know this person at all. I have bought from them. A good place that has charts like this is called thewireman.com. The Wireman, he comes to most of our PanFest. He's out of South Carolina, And if you want to read more about losses and coax and whatnot, he has some interesting information on his site. Like I say, he's a little independent dealer out of South Carolina, but he has a pretty good website. And he's got a lot of different adapters and whatnot as well. Okay, if you want to measure your SWR, how do you do that? Well, there's something called an SWR meter that most people have used. You also can use a directional watt meter. That is where you measure the wattage to the antenna and the wattage being reflected back from the antenna, and that tells you. And in either case, you put it between your transmitter and your feed line. So you put it right at the transmitter because you've got a little bit of coax there, but presumably it would be only 3 feet or so it's not enough to really affect that much. But then you have almost all your coax, feed line, and antenna that's taking place here after the SWR directional watt meter. The SWR meter shows here, you can to the transmitter output, it uses a single meter. Actually, there are 2 meter versions that, and I've got one of those. It has a sensitivity adjustment. You essentially tune it to tune the meter for 100% forward power. And then when you flip the switch, it shows you the reflected power. So it doesn't necessarily measure power in watts. It just measures relative power. Because remember, that's really what SWR is. It's relative power between 2 different forward and reflected. On a directional watt meter, this is one that's all together. It measures both forward and reflected power. The SWR is calculated from the power values of one like this. This is called a bird watt meter. It's considered the gold standard of ham radio watt meters. It's like I say, it's considered the best. It's a little difficult to work with, but it gives you what's considered the best data. This is a less expensive and maybe not quite as accurate, but still an easy one to use. It uses crossed needles, so you've got one that gives you full output and then one that shows you how much being reflected, and that way you can get the where they intersect will give you the SWR. They are in the red line. Antenna Analyzer is another great device that has just recently become cost effective for people. This is an MFJ one here. It measures the SWR, but it also can measure, you can actually use it to plot what we were just showing you before, the SWR curve for the 80 meter antenna. It'll plot that. In fact, some of them now, MFJ doesn't, well, I think they may have one now. But anyway, this one reads out the data and you can plot it yourself. Now they have some with little graphic screens where they plot it for you. So now they're more expensive, obviously, but essentially these are amazing devices to use if you do much antenna work or you just, and now they're common enough that if you don't have one yourself or feel like you can buy one, you can get somebody to come by with one and they'll help you tune your antenna because they are very, very helpful. One of the best tools we've had, and they've really become cost effective over the last probably 10, 15 years. Soldering. We have soldering is a learned skill. In general, soldering is not as tough as soldering a BL259. This shows what's called a cold solder joint. That's where you just essentially get the solder hot, and well, no, this is the cold solder joint here. You just get the solder hot, but you see you don't actually make contact with the lead itself. This is actually a good solder joint here that shows what that is. You always use rosin core solder. Never use acid core. Acid core is used in some cases for galvanized soldering, that kind of thing. It shows solder. Essentially, it's a way to connect 2 wires, mainly electrically, but it can be a pretty decent mechanical connection as well. So, good soldering give you lots of good use over the years. Poor soldering will give you headaches over the life of whatever it is you do. So it makes sense to take your time and make sure you have good soldered connections and if you're putting together something, because if you don't have good, you were mentioning the antenna, intermittent on the antenna. A bad solder connection inside your tuner, a bad solder connection inside with the coax, they can cause you all kinds of problems that can take a good while to fix.
Okay. Antenna polarization is normally used for long-distance, weak signals, single sideband, and CW contacts in the UHF, VHF bands. Horizontal, that's right. When you're using a directional antenna, how might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of sight path?
Without responsibility.
Yeah, it says try to find a path that reflects signals to the repeater, but that's bouncing it off the building, same thing. What is a beam antenna? Their official word is an antenna that concentrates signals in one direction. What types of antennas are a quad, Yagi, and dish? Directional, that's right. Where should an inline SWR meter be connected to monitor standing wave ratio of a station antenna system? In series with the feed line between the transmitter and the antenna. Between the transmitter and the antenna is the main thing to remember there. Which of the following instruments can be used to determine if an antenna is resonant at the desired operating frequency? Well, in this particular case, it could be an SWR meter or whatever, but the answer they want is an antenna analyzer. What instrument other than an SWR meter could you use to determine if a feed line and antenna are properly matched? A directional watt meter. Yeah. Which of the following is the most common cause for failure of coax cable? Moisture, that's right. Why should the outer jacket of coax cable be resistant to ultraviolet light? That's right. It can damage the jacket and allow water to enter the cable. What is the disadvantage of air core coaxial cable when compared to foam and solid dielectric types?
Condensation.
It requires special techniques to prevent water absorption. So yeah, water is the problem.